Tonight, we are stepping gently into the secret life of stars, those distant points of light that glow with a patience far older than anything on Earth, yet still feel familiar every time you look up at the night sky. Stars are simple in their ingredients, yet astonishing in their behavior, shaping the chemistry of galaxies, the color of the night sky, and even the atoms that make up every living thing on Earth. This opening chapter sets the ground beneath us before we rise into the larger story. We will explore what a star truly is, not just as a bright point overhead, but as a vast and intricate object sustained by gravity, heat, and the quiet power of fusion. We will drift through the idea that every star carries a history written in its light, and that understanding that light reveals where it came from, how it changes, and what it will one day become. As we ease into this journey, think of the stars not as distant strangers, but as ancient companions that have shaped the universe since long before Earth formed. Their story is older than oceans, older than mountains, older than every memory our planet has ever held, and yet somehow their quiet glow still reaches us, unchanged across distances so immense they are almost beyond imagination. So let us gently step into that story together and see how something as simple as starlight can reveal the deep workings of the universe. For most of human history, people understood the stars in far simpler terms, interpreting them through the lens of culture, storytelling, and myth. Ancient observers looked upward and saw a sky full of symbols and spirits. Some believed the stars were small fires hanging in the heavens, tended by unseen caretakers. Others imagined them as lanterns carried by ancestors, or as floating embers from the creation of the world. In some traditions, stars were said to be holes in a great celestial fabric, allowing divine light to shine through. Without the tools to study them closely, early humans built meaning from what they could see: patterns, movement, and the quiet constancy of the night sky. Over time, curiosity began to shift into investigation. Philosophers in ancient Greece proposed that stars were distant suns, perhaps made of the same substance as our own. It was a bold thought, far ahead of the technology needed to confirm it. Centuries later, as telescopes improved and scientific understanding grew sharper, it became clear that these faint lights were indeed other suns scattered across enormous distances. Each star was revealed to be a world unto itself, blazing with heat and held together by gravity. The night sky was no longer a simple dome filled with tiny beads of light. It was a vast ocean of suns. The more astronomers learned, the more they realized how varied stars could be. Some burn hot and blue, while others glow gently with a warm red light. Some live for only a few million years, racing through their lives at astonishing speeds. Others linger for trillions upon trillions of years, barely changing at all. A star's brightness, temperature, size, and lifespan are shaped by the environment in which it forms and the mass it begins with. Every star carries a unique story written into its color, its motion, and its light, creating a cosmic landscape far more intricate than anything seen with the naked eye. Even now, when you look up at the night sky, you are seeing only a thin slice of this enormous population. Most stars are too faint or too distant to be noticed without telescopes. Some are hidden behind clouds of dust. Many more have already lived and died, leaving behind remnants that can no longer be seen but still contribute to the fabric of the galaxy. Yet, even this small portion of visible starlight is enough to hint at the immeasurable variety that fills the universe. And this brings us to a natural question, one that lies at the heart of understanding stars themselves. If each point of light represents a distant sun so far away that its details blur into the darkness, then what exactly is inside these radiant objects? What gives them their color, their structure, their glow? And how can such simple ingredients scattered across space create something so powerful and enduring? If you could somehow scoop up a piece of a star, which would be quite the challenge, given the whole blazing hot giant ball of plasma situation, you would find that its ingredients are surprisingly simple. Stars are made mostly of hydrogen, the lightest and most abundant element in the universe. This single ingredient, which can fit many trillions of times into even a modest star, forms the raw material from which starlight is eventually born. Alongside hydrogen is helium, the second lightest element, created as hydrogen fuses together deep within the stellar core. Together, hydrogen and helium make up almost the entire mass of most stars, forming a kind of cosmic simplicity that belies the complexity of what these elements eventually do. But stars also contain tiny traces of heavier elements sprinkled into their vast bodies, like faint seasoning in an enormous soup. These heavier elements were forged long before the star itself was born, created within earlier generations of stars that lived, shone brightly, and eventually died. When those older stars exploded or shed their outer layers, they enriched the surrounding gas clouds with elements like carbon, oxygen, nitrogen, and even iron. New stars formed from this enriched material, meaning that every star carries within it a record of older ones that came before. The universe is, in a way, a grand recycler, forming new suns from the ashes of old ones. Despite the simplicity of these ingredients, the state of matter inside a star is anything but ordinary. Under conditions of immense heat, atoms cannot hold on to their electrons. The electrons are stripped away, leaving behind bare nuclei that move freely in a roving sea of charged particles. This mixture is called plasma, a state distinct from solids, liquids, or gases. Plasma behaves in ways that can feel counterintuitive. It responds to magnetic fields, it carries electrical currents, and it moves with a kind of restless energy shaped by heat, gravity, and internal pressure. Imagine a fluid made of pure electricity and motion, and you are approaching a sense of what plasma feels like inside a star. The quiet, ceaseless transformation of this plasma, driven by gravity and immense heat, sustains everything from the soft glow of a warm summer day to the formation of planets and the evolution of life. The entire journey of a star, from the smallest flicker of energy to the light that traverses billions of miles to reach your eye, is contained within the physics of these simple elements. It is a process where hydrogen becomes helium, helium becomes light, and light becomes the quiet glow that has guided travelers, illuminated myths, and inspired wonder for as long as humans have watched the night sky. And at the heart of it all is one question: what happens deep inside a star when hydrogen begins to change? This gentle exploration of the star's essence is a reminder that the most profound things often begin with the most fundamental building blocks, assembled with patience across the quiet stretches of cosmic time. When you look up at the night sky, it is easy to imagine only a handful of stars scattered across a quiet stretch of darkness. They seem so small, so faint, so gentle, that it almost feels as though you could count them if you really tried. But those tiny pinpricks of light are only the beginning of what is out there. Astronomers estimate a single large spiral galaxy can hold hundreds of billions of stars, each one a vast sphere of glowing matter, each with its own history and its own future. And beyond that single galaxy are countless others, arranged across the cosmos like a slow drifting snowfall that extends in every direction. The universe is not just sprinkled with stars, it is saturated with them. Our own galaxy, the Milky Way, is one example. From the outside it would resemble a grand spinning disk made of long sweeping spiral arms that wind outward from a glowing central bulge. These arms are not empty spirals of dust, they are busy avenues where new stars form, where clusters take shape, and where young suns begin their long luminous lives. Closer to the galactic center, stars are packed together more tightly, creating a dense region that glows with an older, steadier light. Surrounding all of this is a large, faint halo that contains ancient, long-lived stars and stellar remnants drifting like quiet sentinels around the brighter disk. When you imagine a galaxy from afar, imagine a slow whirl of light and dust, with stars arranged in patterns shaped by gravity and time. Yet, from Earth, all of this grandeur collapses into the smallest of details. Stars look like delicate points of light because they are incredibly far away. Even the nearest star beyond the Sun is so remote that its light takes over 4 years to reach us. The vast majority are far, far more distant than that. If you held out your hand and covered the sky with a fingernail, the tiny portion of space hidden behind it could contain millions upon millions of stars. Their light travels across unimaginable distances before it reaches Earth, shrinking them in appearance until they look almost fragile. In our reality, each is huge, powerful, and complex. But the universe keeps its scale hidden behind long distances. The idea of billions of stars can be difficult to fully process, and the concept of the observable universe expands that even further. The observable universe contains everything whose light has had enough time to reach us since the beginning of cosmic expansion. When astronomers describe this region, they are not setting a boundary for the universe itself, only for the part we can currently see. Light from the farthest visible galaxies has traveled for more than 13 billion years before reaching our telescopes, crossing expanding space with unwavering patience. When that ancient light touches Earth, it carries with it the faint memory of what those galaxies looked like, long before our solar system even existed. It is a reminder that the heavens are not just wide, but profoundly old, and that the light we see tonight is a message from distant epochs. The depth of this age is central to the quiet appreciation of starlight. When you consider the vast stretches of time that light has taken to cross the cosmos, the simple act of looking up becomes a moment of connection to a past almost beyond imagining. The light itself is a kind of fossil, a remnant from a time when galaxies were forming, stars were igniting, and the universe was much younger and denser. Every photon that finally enters your eye carries with it an imprint of the star that created it, filtered by the vastness of space and time. This journey of light helps explain why stars appear as they do. The faint shimmering, the occasional twinkle, is not necessarily inherent to the star, but a result of its long journey. The twinkling, for instance, is caused by Earth's atmosphere, as tiny movements of air refract the delicate starlight, making the distant point of light appear to dance. Stars that are looser, like the planets, shine with a steadier glow because their light rays are wider and less affected by atmospheric disturbance. The immense distance, coupled with the subtle motions of our own world, transforms powerful suns into gentle shimmering points, which only deepens the sense of quiet wonder. Imagine the universe as a grand, slowly turning mechanism, where every star is a meticulously placed gear, contributing to the movement and the light of the whole. Our galaxy, the Milky Way, is one such mechanism, where stars are constantly being born in the busy spiral arms and older stars drift in the more stable central bulge and the surrounding halo. This organized chaos, driven by the patient force of gravity, keeps the entire system in a slow, elegant motion. We are situated within one of these spirals, unable to see the whole structure at once, only the slice of light we perceive as the Milky Way band across the night sky, a soft, glowing reminder of the immense stellar population surrounding us. In this grand scale, the difference between what we see and what truly exists is enormous. The observable universe continues to expand, and with it, the number of stars we know to exist. Yet, for all the billions of suns scattered across the darkness, the fundamental physics remains the same. The laws of gravity, heat, and fusion that govern our familiar sun also govern the brightest blue giant or the faintest red dwarf in a galaxy billions of light years away. This universality is perhaps the most peaceful thought of all, that even in the face of incomprehensible scale, the underlying order of the cosmos remains consistent and beautifully simple. The quiet glow of a single distant star is a message confirming that the same enduring principles govern all the countless suns that fill the endless sky. The stars are a vast, immeasurable population, yet each one is a family, a world of its own, bound by the same quiet forces. If you could peer into the blazing heart of a star, past the blinding surface and the immense heat, you would encounter a region defined by a profound and unexpected simplicity. Despite the staggering power and complexity of a star's light, its core ingredients are remarkably few and familiar. Stars are overwhelmingly composed of the lightest and most abundant elements in the universe, an elegant testament to how the most powerful phenomena often arise from the most fundamental building blocks. The primary ingredient is hydrogen, the simplest of all elements. A single hydrogen atom consists of just one proton in its nucleus, often accompanied by a single electron orbiting it. This simple structure, repeated countless trillions of times, forms the raw foundational material of almost every star in the cosmos. In fact, hydrogen is so dominant that it often makes up about 3/4 of a star's entire mass, creating a vast reservoir of fuel. Imagine a star as an enormous cosmic vessel, filled mostly with this incredibly light gas, the raw material from which all the star's light and heat will eventually be born. The second key ingredient is helium, the element that arises directly from the stellar process itself. Helium is the immediate product, the ash, if you will, created as hydrogen atoms are transformed within the star's core. Compared to hydrogen, helium is heavier, with a nucleus typically containing 2 protons and 2 neutrons. Although helium is the second most common element in the universe overall, that star created much of the helium found in a star, patiently accumulating at the center over billions of years. Together, hydrogen and helium constitute nearly the entire mass of a star, forming a kind of elegant simplicity that is at the heart of stellar physics. But stars are not purely composed of each 2 light elements. They also contain tiny traces of everything else, elements that astronomers collectively call metals, though this term applies to any element heavier than helium. These heavier elements are sprinkled into the vast, luminous body of the star like faint seasoning in an enormous cosmic soup. Their presence is a quiet clue, a subtle record of older stars that lived, shone brightly, and eventually died. These heavier elements, things like carbon, oxygen, nitrogen, and even iron, were forged in earlier stellar generations. When those older, massive stars ended their lives in spectacular explosions, or when smaller stars shed their outer layers, they enriched the surrounding gas and dust clouds with these elements. New stars, including our own Sun, formed from this enriched material, meaning that every star carries within it a small but significant record of its predecessors. The universe is, in this way, a grand recycler, constantly forming new suns from the ashes and remnants of old ones. This cyclical process links every star, every planet, and every living thing to the ancient chemistry of the cosmos. Despite the simplicity of the star's composition, the state of matter inside it is anything but ordinary. Under conditions of immense heat and staggering pressure, atoms cannot hold on to their electrons. The electrons are stripped away, leaving behind bare nuclei that move freely in a roving, energetic sea of charged particles. This mixture is called plasma, a state of matter distinct from solids, liquids, or gases. It is often described as the fourth state of matter, and it behaves in ways that can feel almost counterintuitive. The plasma inside a star is constantly churning. Heat from the core causes pockets of plasma to rise, while cooler regions sink downward, creating slow-motion convection currents, similar to the gentle bubbling of boiling water, but on an unimaginably grand scale. This internal turbulence twists through the interior like gentle, powerful storms, shaping magnetic fields and stirring material in slow, powerful cycles. This motion is continuous, unending, and deeply tied to the way stars transport the immense energy generated in their centers outward into space. The heat within a star varies dramatically, dropping steadily from the core to the outer layers. At the core, where gravity compresses matter into an incredibly dense region, temperatures reach tens of millions of degrees, enough to force hydrogen nuclei close enough together for fusion to occur. As you move outward from this inner furnace, temperatures gradually fall. The outer layers, despite looking incredibly bright and glowing, are comparatively cool, reaching only a few thousand degrees at the visible surface. This is a dramatic gradient, a steady decline from the extreme to the merely scorching. Because of this temperature structure, stars do not possess a solid surface. The bright layer you see when you look at a star is not a crust or a shell. It is simply the point where the plasma becomes thin enough for light to escape freely into space. This region, called the photosphere, gives stars their visible glow but has no solidity to it. If you tried to step onto a star, you would fall through this glowing layer as though through a shimmering fog surrounded by superheated plasma that grows denser and hotter as you sink inward. Stars are not rigid objects. They are more like luminous, restless storms held together only by gravity and the delicate balance between outward pressure and inward collapse, these simple ingredients, hydrogen and helium, and the extreme state of matter they form, set the stage for the immense process that powers every star. The extreme conditions are not just impressive numbers, they are crucial. WY. Without temperatures high enough and pressures strong enough, the hydrogen inside a star would remain inert, floating in quiet plasma forever. But in the heart of a star, the environment becomes so intense that hydrogen nuclei are pushed close enough to begin the slow, steady process of fusion, releasing the energy that supports the star against gravity and sends light outward across the cosmos. This quiet, ceaseless transformation is the star's constant work, sustaining everything from its structure to the distant light that reaches us tonight. Long before a star ever begins to shine, long before it grows warm enough to glow or bright enough to be seen from across the galaxy, its story begins in a place that appears completely lifeless. These birthplaces of stars are known as giant molecular clouds, and despite the dramatic name, they are some of the coldest and darkest regions in the entire cosmos. They stretch across many light years, containing enormous amounts of hydrogen gas mixed with dust, drifting slowly through the galaxy like faint, shadowed continents made of smoke. If you could see one up close, it would not look bright or fiery. Instead, it would be dim and quiet, with dense knots of material hidden inside a veil of darkness. These clouds are so cold that molecules can survive without being torn apart, and so thick with dust that even starlight struggles to pass through them. They are interstellar nurseries, vast and tranquil, where the material needed for a star to form waits patiently in the profound cold. Within these dark regions, stillness is only an illusion. Although the clouds appear calm, they are constantly stirred by subtle turbulence, slow rolling motions caused by differences in density, temperature, and magnetic fields. Over time, these gentle disturbances can push material together, forming small pockets where gas becomes slightly denser. Its surroundings. Sometimes the push is far stronger. Nearby stars may end their lives in spectacular explosions, sending out expanding shock waves that sweep through the cloud and compress parts of it like a giant cosmic hand patting flour into clumps. When turbulence, collisions, or these shock waves nudge a region past a certain threshold, gravity begins to take over. Once gravity gains the advantage, collapse begins. It is not a sudden drop or a dramatic plunge, but a slow tightening, like a long breath drawn inward. Gas begins to fall toward the center of these dense pockets, causing them to grow ever more compact. As more material gathers, gravity strengthens, pulling in even more gas. This process is steady, relentless, and patient, unfolding not in days or years, but over many thousands and millions of years. This slow accumulation creates a growing core of matter, still cold compared to what it will one day become. This core is warming bit by bit as the increasing pressure from the material falling in raises its temperature. This growing core is what astronomers call a protostar, the earliest stage in a star's life. A protostar is not yet a star in the usual sense. It does not produce light through nuclear fusion, and it does not shine steadily. Instead, it glows weakly from the heat generated by compression, much like hands warming from being pressed together tightly and rapidly. The gas around the protostar continues to fall inward, but not all of it heads straight for the center, because even the gentlest rotation speeds up as a cloud collapses. The infalling material flattens into a swirling structure known as an accretion disk. The protostar sits at the middle of this disk, drawing in matter like a quiet whirlpool surrounded by a wide, thin ring. These disks may look delicate in illustrations, but they are enormous, often stretching across distances f.a.r. wider than entire planetary systems. Within them, dust grains collide and drift, gradually sticking together. In time, they can form the seeds of planets, moons, and asteroids. This means that the earliest building blocks of planetary systems begin to assemble while the star at the center is still forming. The creation of planets is, therefore, a simultaneous event with the birth of the star itself happening in the surrounding material that did not quite fall into the stellar core. Meanwhile, near the poles of the protostar, material that cannot easily fall in is redirected into narrow jets that stream outward in opposite directions. These jets carve paths through the surrounding cloud, sometimes stretching for many light years, glowing faintly as the fast-moving material heats the gas it passes through. Despite their energetic appearance, these jets form naturally from the complicated dance of rotation, magnetic fields, and gravity at work around a forming star, acting as a kind of release valve for the immense forces gathered at the core. As collapse continues, the temperature at the center of the protostar rises steadily. Gravity pushes the particles closer together, increasing pressure and forcing the dense core to heat up. Over long stretches of time, this warming accelerates, creating a slow march toward a critical threshold. Deep in the core, hydrogen nuclei are packed so tightly that they begin to brush close enough for the possibility of fusion to emerge. The temperature must rise to millions of degrees before hydrogen can transform into helium. It is not a moment of sudden ignition like a match striking. Instead, it is a gradual tipping point, a quiet transition where the first fusion reactions begin to take place, releasing small amounts of energy that feed back into the surrounding material. As more fusion reactions occur, the core becomes hotter still, eventually reaching a steady enough rate that the young star begins to support itself. The inward pull of gravity balances with the outward push of energy produced by these reactions. It is in this delicate state of balance that a star is truly born. The protostar phase ends, and the main sequence phase begins, a long stable era where the star will spend most of its life quietly fusing hydrogen into helium and shining steadily into the cosmos. What makes this process remarkable is not its drama, but its patience. Nothing about a star's formation happens quickly. The collapse of a cloud into a protostar takes an immense amount of time, and the journey from protostar to fully fledged star takes even longer. From a human perspective, these events unfold so slowly that entire civilizations could rise and fall while a young star is simply gathering itself together. It is a reminder that the universe has no need to hurry. Stars emerge at their own pace, shaped by vast clouds, quiet motions, and the gentle pull of gravity that works tirelessly over unimaginable spans of time. By the time starlight finally appears, the process has already been unfolding for many millions of years, a long and patient awakening. And when that first steady glow reaches into the darkness, a new point of light enters the galaxy, ready to begin its long and luminous journey through cosmic history. Deep in the center of a star, far beneath the glowing layers that we see from the outside, there is a region where the conditions are so intense that normal matter behaves in extraordinary ways. The hydrogen that makes up most of the star is packed together with unimaginable force, squeezed by the enormous weight of everything above it. Each particle is surrounded by staggering heat, moving with such speed that it becomes almost impossible to picture in everyday terms. Yet within this extreme environment, something elegant begins to happen. Slowly, steadily, and without any grand explosion, hydrogen starts to transform into helium. To understand this transformation, it helps to picture hydrogen not as a gas in the way we experience it on Earth, but as tiny nuclei moving through a superheated sea of plasma. Each nucleus consists of a single proton, and under normal conditions, those protons would fiercely repel each other. They carry the same electrical charge, and like two identical magnets with the same poles facing, they push apart with determination. This natural repulsion is a powerful barrier that prevents most atoms from simply fusing together. For two hydrogen nuclei to fuse, they must be forced so close that they can overcome this natural electrical repulsion. Only at the heart of a star, where pressure is overwhelming and temperatures reach many millions of degrees, can this become possible. Why such intense conditions? Because the particles need tremendous energy just to get close. The heat inside the core causes them to move at staggering speeds, and the pressure caused by the star's own weight forces them into a crowded environment where collisions happen constantly. Even with this chaos, most of these collisions do not lead to fusion. The protons simply bounce off one another, repelling each other as they always try to do. But every now and then, something remarkable occurs. The classical picture would say fusion should almost never happen because the repulsion is too strong. But the universe has a quiet trick hidden within the rules of quantum mechanics. There is a concept known as tunneling. And although it is usually written using symbols and equations, the basic idea can be expressed in simple words. Instead of imagining particles as tiny billiard balls that must climb over a barrier of electrical repulsion, imagine them as objects that sometimes, very rarely, slip through the barrier instead. They do not smash through it. They do not break it. They simply appear on the other side without needing the full energy required to leap over it. It is as if nature provides a small shortcut, one that is improbable but not impossible. And because the core of a star contains so many particles colliding so frequently, even rare events can happen often enough to matter. Through this quiet process, two protons occasionally slip close enough together that a transformation can begin. The exact sequence of steps is complex, involving gentle shifts in particle structure, but the end result is that hydrogen nuclei slowly merge to form helium. The change is small on a particle-by-particle basis, but when it happens countless times throughout the core, the combined effect becomes profound. With each successful fusion event, a tiny amount of mass is converted into energy. This energy does not burst outward in a violent flash. Instead, it appears in the form of light and motion on the smallest scales, spreading through the surrounding plasma. Imagine millions upon millions of tiny sparks flickering in the dark, each too small to notice individually, but together, over time, they become the star's heartbeat. The energy released by these microscopic transformations is what eventually becomes the light that warms planets, illuminates night skies, and travels across interstellar space. The process is not chaotic or explosive. It is steady, continuous, and astonishingly gentle when viewed up close. A star is not powered by fire, it is powered by patience. This steady energy production creates an extraordinary balance inside the star. As the core generates light and heat, this energy pushes outward. At the same time, gravity exerts a pull inward, trying to compress the star further. These two forces meet in perfect balance, each countering the other. It is this balance that allows a star to remain stable for billions upon billions of years. If the energy production decreased, gravity would begin to compress the star more tightly, increasing the temperature and restoring the fusion rate. If energy production increased too much, the star would expand and cool slightly, slowing the reaction rate. But in a well-behaved star like the Sun, these changes balance themselves naturally. The star constantly adjusts like a tightrope walker, maintaining steady footing with tiny unconscious shifts. This equilibrium is one of the most beautiful aspects of stellar physics. It means that a star is neither collapsing nor exploding, it simply shines. The outward flow of light matches the inward pull of gravity with exquisite precision. Fusion also determines how long a star can live. A larger star burns through its hydrogen quickly because its enormous gravity demands a stronger outward push to maintain equilibrium. A small star burns hydrogen slowly and steadily, barely sipping its fuel, which is why some tiny red dwarfs are expected to shine for trillions of years. But regardless of size, every star depends on fusion to keep gravity at bay. Without the energy produced in the core, the star would collapse under its own weight, compressing until something entirely different emerged. In many ways, a star behaves like a living organism with a metabolism powered by fusion. It consumes hydrogen, produces helium, releases energy, and maintains a steady internal environment. The process is not alive in the biological sense, but it shares the same sense of ongoing continuity. Fusion is the star's constant work, always happening, always renewing the outward pressure that prevents collapse. This quiet, ceaseless transformation sustains everything around it. So deep inside the core, hydrogen slowly becomes helium, and helium gather. As a quiet record of the star's age. Over billions of years, the balance between gravity and light remains locked in place, shaping the star's appearance and guiding the rhythm of its life. In this partnership between inward pressure and outward energy, a star finds the stability it needs to shine across the cosmos. And as long as fusion continues, the star's heart keeps beating, steady and bright, illuminating the universe with a light that began in the smallest and most unlikely of quantum events. The light that leaves a star and eventually reaches your eyes begins its life in a place that is almost nothing like the glowing surface we see from far away. Deep in the core, where hydrogen becomes helium and the star generates its energy, photons are created in enormous numbers. But these newborn photons do not immediately begin their journey into space. Instead, they face a long wandering path that is so slow and chaotic that it almost defies intuition. Light produced in the core takes an extraordinary amount of time to reach the outer layers, not because the distance is large, but because the environment is so crowded and dense that each photon is stopped almost instantly after it forms. Inside the core, matter is crammed together under enormous pressure. There is no empty space, no gentle corridors for light to slip through. Photons collide with particles almost as soon as they appear, being absorbed and then remitted in a different direction. This absorption and remission does not propel them outward in a straight path. Instead, it sends them on a kind of random walk, scattering in every direction. A single photon might travel only a tiny fraction of a millimeter before being caught again. Over time, this process repeats not hundreds or thousands, but many trillions of times. The photon's movement becomes a slow, zigzagging dance that more closely resembles energy in a crowd than racing outward. The region where this slow diffusion dominates is known as the radiative zone, and it occupies much of the star's interior. In this zone, the plasma is so dense and so tightly packed with ions and electrons that photons rarely move freely. They bounce around in a slow and intricate pattern, constantly exchanging energy with the surrounding matter. Even though each photon travels at the speed of light between interactions, the path as a whole becomes incredibly sluggish. It is one of the great contrasts of stellar physics. Light itself is incredibly fast, but inside a star, light's journey is almost unimaginably slow. The time it takes a photon to move from the core to the surface varies with the star's structure. But for a star like the Sun, estimates suggest that this journey can take hundreds of thousands of years. Imagine that. The sunlight warming your face on a quiet afternoon may have begun its journey when early humans were still learning to shape simple tools. It is almost poetic that the light we see today began its life in an age long gone, drifting through the star in countless steps before finally escaping. As photons move outward, they eventually reach a region where the density begins to decrease and the star's behavior changes. This is the beginning of the convective zone, where the plasma becomes cooler and thicker relative to the layers below. Here, energy can no longer easily travel by radiation alone because the plasma absorbs light more readily. Instead, movement takes over. Large pockets of hot material rise upward, carrying heat with them, while cooler material sinks downward to take their place. It is a slow-motion churning, not violent or chaotic, but steady and rhythmic, like water heating in a pot before it comes to a boil. This convective motion carries energy far more efficiently through the outer layers. And as these currents reach the surface, they create patterns of rising and sinking material. When viewed closely, this creates a textured appearance known as granulation. Each granule is a cell of hot plasma rising to the surface, glowing brightly before cooling slightly, and sinking back down around its edges. When astronomers observe a star with powerful instruments, this pattern of tiny shifting cells looks almost like a field of glowing, shimmering grains. It gives the star a gently boiling appearance, not in the violent sense of boiling water, but in the softer, more delicate sense of a shimmering liquid full of subtle, constant motion. At the very outer edge of the star, the plasma becomes thin enough for photons to finally break free. In this region, known as the photosphere, light is no longer trapped by dense material. Photons that reach this point can travel outward without being captured again. After spending so long bouncing through the interior, their final escape into open space is instantaneous. Once free, they travel at the familiar speed of light, racing across the void for years, centuries, or even billions of years, depending on their destination. The light from a star is not a single type of light, but a spectrum of different forms of energy. Visible light is only a narrow slice of what a star produces. There is ultraviolet light, which carries more energy and can ionize atoms in the upper atmospheres of planets. There is infrared light, which carries warmth and is essential for maintaining the temperatures of planetary surfaces. There are radio waves, the gentle giants of the electromagnetic family, carrying long, soft wavelengths that travel easily through cosmic dust. There is even high-energy radiation, such as X-rays and gamma rays, although much of this is produced in specialized environments like stellar flares or dense stellar remnants, RAT. Than in the quiet flow of everyday starlight, each type of light tells a different story. Infrared light reveals cooler regions like dust clouds where new stars may be forming. Ultraviolet light traces the energetic surfaces of hotter stars. Radio waves pass through places that visible light cannot, allowing astronomers to map the structure of galaxies. All of these forms of light originate in the same fundamental processes taking place deep within the star, shaped and filtered by the star's layers as they rise outward. Once a photon escapes, it begins a journey that may carry it across interstellar space for an astonishing amount of time. Some photons will reach nearby planets within minutes. Others will travel for thousands or millions of years before striking a grain of dust or being absorbed by a distant world. Many will continue onward for billions of years, long after their parent star has changed or even ceased to exist. The universe is full of these silent travelers, each a tiny messenger from the heart of a star. It is remarkable to think that something so fleeting, a single particle of light, can carry within it a record of the processes that created it. When that light reaches a telescope or the human eye, it reveals information about temperature, motion, composition, and age. It is one of the quiet wonders of the universe that a photon born in a violent, crowded core can eventually become a gentle glimmer in the night sky, illuminating a moment far removed from its origin. So when you look at a star, you are seeing the final chapter of a story that began in unimaginable heat and ended in calm starlight. The glow that reaches you is not simply brightness, it is the accumulated result of countless collisions, slow diffusion, churning motion, and patient escape. Every ray of light is a journey, and every journey begins far deeper within a star than first. Impressions suggest. The vast patience of the light's journey is perhaps the most soothing part of all, a testament to the fact that even the fastest thing in the universe can move with quiet slowness when faced with the immense density of a star. When you look at the night sky, the stars may all appear to share the same gentle silvery glow. They seem uniformly pale and distant, as though color is something reserved for sunsets, flowers, and the occasional stubborn traffic light. But stars are not colorless. Each one carries its own hue, shaped by its temperature, its age, and the path its light takes to reach your eyes. If you were able to drift a little closer, or if human eyes were more sensitive, you would see a sky sprinkled with subtle reds, warm golds, icy whites, and deep celestial blues. Star color is not an artistic flourish. It is a clue, revealing the conditions at its surface and offering a gentle thread that leads directly to the physics within it. The idea that temperature determines color may feel surprising at first. On Earth, we tend to associate hotter things with a deeper red. Heated metal turns from red to orange to yellow as it warms, and anything blue usually feels cold. But the universe has its own way of doing things. A star's color follows a smooth, natural sequence based on how hot its outer layers are. The cooler stars, with surface temperatures only a few thousand degrees, glow with a soft red light. As temperature increases, the color brightens into orange and then into a gentle yellow. Slightly hotter stars appear white, and beyond that, at even higher temperatures, they glow with a pale blue light. Rather than red meaning hottest, it is blue that marks the most intense heat. The colors are subtle when viewed from far away, but each one is honest and precise, shaped by the star's own warmth. A calm way to understand this is to imagine a flame. A candle flame has a warm yellow tone, but the base of the flame, where it is hottest, shifts toward a pale blue. Stars follow the same principle, just on a scale far more immense. A red star is not cold, it is still thousands of degrees. But compared to a blue giant, which may burn at tens of thousands of degrees, the red star's light is simply the result of a gentler, cooler temperature. The color temperature sequence is smooth and intuitive once you release the everyday associations we tend to carry. A star's glow is simply the universe's quiet way of telling you how hot its surface is. One of the reasons hotter stars appear bluer lies in the nature of light itself. Light is made of waves, and the hotter a star becomes, the more its energy changes into shorter wavelengths. The shorter wavelengths appear blue or even blue-white to our eyes. Cooler stars emitting light with longer wavelengths present themselves as red or red-orange. None of this requires complex calculations to appreciate. It simply means that as temperature rises, a star's glow changes shade in a predictable, gentle procession from red to blue. Many artists spend years learning how to blend colors smoothly. Stars do it naturally, following the fundamental laws of energy emission. Although a star's color begins with temperature, it is not the only factor influencing what we see. Light must travel across space before it reaches Earth, and along the way, its color can be softened or shifted by the material it passes through. Interstellar dust, spread thinly across great distances, tends to scatter blue light more effectively than red. As a result, some stars appear slightly redder than they actually are. Their blue light is scattered away before it can reach us. This process is similar to the way Earth's sky appears blue during the day because the atmosphere scatters sunlight, although on a ch larger cosmic scale. Space is mostly empty, but even the smallest amount of dust can gently shift the colors of distant stars. Closer to home, Earth's atmosphere adds its own influence. When a star is high in the sky, its light travels through a relatively thin layer of air, and the color remains almost unchanged. But when a star sits low on the horizon, its light must travel through a larger stretch of atmosphere. This scatters more of the bluer wavelengths, giving the star a warmer, redder appearance. It is the same effect that turns sunsets golden and makes the moon look orange when it rises. The star itself has not changed, but the path its light takes has added its own gentle filter. A star's color is not fixed for its entire life. As stars age, their temperatures change and their colors shift with them. A young star, just beginning its long stable phase, may glow with a clean white or pale yellow light. Over billions of years, as it converts hydrogen into helium and its internal balance changes, it can slowly warm or cool depending on its mass. When a star like the Sun nears the end of its stable life, it expands into a red giant, cooling at the surface and taking on a deeper reddish hue. A massive star, by contrast, may spend much of its life shining with an intense blue glow before rapidly burning through its fuel and ending its life in a dramatic transformation. Color becomes a quiet marker of time, one that reveals a star's place in its long journey. Perhaps the most familiar example of this color-temperature relationship is the Sun. To the human eye, the Sun often appears yellow, especially when it hangs low in the sky or when atmospheric scattering lends its glow a gentle warmth. But if you could view the Sun from outside Earth's atmosphere, its color would look quite different. It would appear closer to white because the Sun emits a balanced mixture of wavelengths across the visible spectrum. The yellow appearance is largely an atmospheric effect, not an intrinsic property of the Sun itself. In truth, the Sun is a white star with a hint of soft gold only when filtered through the air of our planet. Understanding the colors of stars adds a layer of depth to the night sky. That faint red point may be a cool, ancient star nearing the end of its life. That pale blue glimmer may be a young, massive star burning fiercely with a surface temperature far greater than the Sun's. The white stars scattered across the sky are often those in their long, stable middle age, shining quietly and consistently. Each color is a clue, a whisper from the star about its temperature, age, and energy. So the next time you look at a star, consider the long journey its light has taken and the story tucked within its hue. A star's color is not just a shade. It is a signature, a message written in light, revealing the conditions of worlds impossibly far away. Stars do not speak in words, but they do speak in color. And once you know how to listen, the night sky becomes a far more expressive place. Its silent colors are a serene form of communication, connecting the extreme heat of a distant core to the gentle perception of the human eye. Inside every star is a quiet internal structure that never appears in the soft glow we see from far away. A star may look smooth and uniform from the outside, but beneath that shining surface is a layered interior. Each region is shaped by different temperatures, different densities, and different ways of moving energy from the center to the edge. These layers are not hard boundaries or solid shells. Instead, they blend gently into one another, like the gradual shift in color that comes with sunrise. To understand how a star truly works, it helps to take a calm, unhurried tour from the core outward, exploring how each layer contributes to the star's overall rhythm. At the very center lies the core, the beating heart of the star. It is the smallest region in terms of size, but the largest in terms of energy. Here, temperatures reach many millions of degrees, and pressures grow so extreme that hydrogen nuclei are forced close enough together for fusion to begin. The core is where all the star's energy is created, not in sudden bursts, but in a steady stream of tiny fusion reactions that unfold constantly across countless particles. It is a region of intense heat and relentless activity, where the dense, shimmering sea of plasma glows with energy that will eventually journey outward to become starlight. Surrounding the core is the radiative zone, an expansive layer where light slowly diffuses outward. The plasma here is tightly packed, so photons that emerge from the core cannot simply travel through. They are absorbed and then remitted countless times, scattering in all directions. Even though light moves at the fastest speed allowed by nature, the density of this region slows its journey dramatically. A photon can take hundreds of thousands of years to wander through the radiative zone, bouncing from particle to particle in a long and patient migration. It is a region governed by radiative transfer, where light itself becomes the main carrier of energy, patiently working its way through the dense matter. Further outward, the star's character begins to change. As the density drops and the plasma becomes cooler, energy can no longer travel primarily by radiation. Instead, movement takes over through convection. This region is known as the convective zone, and it behaves somewhat like a vast, slow-motion pot of simmering liquid. Hot plasma near the bottom of the convective zone becomes buoyant and rises upward. As it approaches the cooler layers above, it releases some of its heat and begins to sink again. These rising and falling currents create a continuous circulation pattern that carries energy efficiently toward the surface. This convection is not turbulent in the violent sense, but it is dynamic and constantly shifting. Each cell of rising plasma may take days or weeks to travel upward, forming immense structures that dwarf even the largest planets. The movement is steady and rhythmic, a quiet churning that shapes the star's surface appearance. If you could hover above the convective zone and observe it directly, you would see enormous cells of bright, hot plasma rising, bordered by darker lanes where cooler material sinks. This behavior sets the stage for the surface patterns we observe in stars like the Sun. At the outermost visible layer lies the photosphere, the place where the star's light finally escapes into space. The photosphere is not a solid surface, though it looks smooth from afar. It is simply the region where the plasma becomes transparent enough for photons to travel outward without being trapped. When astronomers capture detailed images of the Sun's photosphere, they can see granulation, a mosaic of bright patches and darker edges created by the convection below. Each bright granule is an upwelling of hot plasma, while each darker lane marks the sinking of cooler material. This gives the photosphere a gently modeled appearance, as though the star were a glowing ocean with subtle waves constantly appearing and fading. Yet, stars are not quiet spheres. Beneath the surface, waves and oscillations travel through the stellar interior, causing subtle changes in brightness and motion. These waves behave somewhat like sound waves traveling through air, except they move through the star's plasma. Some waves travel deep into the core, bouncing off dense layers and returning to the surface. Others skim along the outer edges, ping the movement of the photosphere. These oscillations are far too subtle to notice with the naked eye, but sensitive instruments can detect them as tiny rhythmic variations in brightness or shifts in the star's light. These vibrations reveal a surprising amount of information. Just as earthquakes help geologists understand Earth's internal structure, waves inside stars, sometimes casually called starquakes, allow astronomers to probe the layers within a star. Studying these vibrations is known as asteroseismology, a field that listens to the internal pulses of stars to learn how they are built. By observing how different waves move through the star, scientists can deduce the temperature of the core, the density of each layer, the star's age, and even the proportions of elements inside it. The idea is wonderfully intuitive once explained. Waves travel differently through materials of different densities and temperatures. By measuring the patterns of those waves at the surface, astronomers can work backward to determine what the waves encountered on the inside. It is similar to hearing a musical instrument and inferring its shape from the quality of the sound. A flute and a cello produce different tones because of their structure. In the same way, a young hot star will vibrate differently from an old, slowly cooling one. Asteroseismology turns starlight into a kind of cosmic music, offering hints about the hidden architecture within. These oscillations confirm that the star's interior is anything but silent. Energy moves, waves bounce, and plasma rises and falls in vast circulations. The layers work together to transport the star's energy outward, forming a complex but harmonious structure. The core makes the energy. The radiative zone diffuses it outward, the convective zone carries it through motion, and the photosphere releases it into the universe. Each region, P, lays its part, and each part is essential. Despite the immense forces and complex physics involved, a star's architecture remains beautifully ordered. It is a layered system that has evolved naturally from the rules of energy transport, gravity, and heat. The star does not consciously organize itself, yet the structure emerges with remarkable consistency. From the smallest red dwarfs to the most luminous giant stars, this quiet pattern appears again and again, a universal blueprint shaped by the laws of physics. Within that calm, layered architecture, starlight is born, guided, and released into the universe, completing its long journey from the core to the outer darkness. When you look at a star, it seems to offer only one piece of information, a steady glow of light from far away. It appears simple, perhaps even plain, yet hidden within that glow is an astonishing amount of detail, more than any telescope could ever capture through images alone. Stars speak through their light, and astronomers have learned to listen. With the right tools, the faintest ray of starlight becomes a message filled with structure, color, clues, and quiet signatures of what is happening on the star's surface and deep within its interior. It is one of the loveliest ideas in all of astronomy. Even a distant star, one that no human could ever hope to visit, can tell us everything we need to know simply by shining. The key to this cosmic conversation lies in something called spectral lines, which might sound intimidating at first, but are in truth very friendly once understood. When starlight is spread out into a rainbow, either by a prism or a special instrument known as a spectrograph, it reveals smooth bands of color. But within those bands are tiny, precise gaps where certain colors are missing. These gaps form thin, dark lines in the rainbow, like delicate scratches on glass. They appear because atoms in the star's outer layers absorb specific colors of light. Each type of atom, whether hydrogen, helium, oxygen, iron, or anything else, has its own unique pattern of colors that it absorbs or emits. These patterns are as distinctive as fingerprints. If an atom could sign its name, it would do so with a set of spectral lines. This behavior comes from the way electrons inside atoms can only occupy certain, fixed energy levels. When an electron absorbs a photon of precisely the right color, it gains energy and can jump from one level to another. That means the corresponding color of light disappears from the rainbow, creating a dark absorption line. Later, when electrons fall back to their original levels, they emit light of very specific colors, creating bright lines in other circumstances. What matters most is that each element has its own unique pattern. Hydrogen creates one set of lines, helium another, iron another. No two are the same. This allows astronomers to read the star's composition almost as easily as reading a recipe. From these lines, astronomers can learn far more than just what a star is made of. The thickness and shape of each line reveal temperature, because atoms behave differently at different levels of heat. Some lines broaden when the star spins rapidly, allowing us to measure its rotation speed. Even though we cannot see it turning, certain patterns shift in subtle ways. If the star has strong magnetic fields, even the density of the star's outer layers can leave a fingerprint in the way the lines appear. It is remarkable that such tiny features can reveal so much about something as vast as a star. But stars are generous in sharing their secrets through light. One of the most useful tools in this gentle conversation is the Doppler effect, which can be explained without any mathematical symbols at all. If a star is moving toward you, its light waves become slightly compressed, shifting the spectral lines toward the blue end of the rainbow. If the star is moving away from us, the waves stretch out, shifting the lines toward the red end. This shift is small, almost imperceptible without instruments, but it is powerful. By measuring these changes, astronomers can determine whether a star is approaching or receding, and how quickly. This method is so sensitive that it can even reveal the influence of planets orbiting the star. A star with a planet will wobble slightly as the planet's gravity tugs it around, creating tiny rhythmic shifts in the spectral lines that betray the planet's presence. It might seem surprising that this technique works for stars that are thousands of light years away. After all, by the time the light reaches us, it has traveled for so long that you might think the information would get blurred or lost. But starlight is remarkably resilient. The pattern of spectral lines remains intact as the light crosses the vast emptiness of space. Even interstellar dust or gas cannot change the fundamental structure of those lines, only dim the light slightly or shift its color. That means a telescope on Earth can analyze starlight in the same way whether the star is close or unimaginably distant, because every star contains a mix of elements, and every star moves in its own slow dance through the galaxy. Each one creates a distinctive spectrum. This allows astronomers to treat spectra like signatures. If you gather the spectra of many stars, you can identify which ones are metal-rich, which are metal-poor, which are young, old, calm, or unstable. You can learn how fast they spin, how strongly their magnetic fields behave, and whether their surfaces are turbulent. You can even classify them into families, grouping stars with similar spectral patterns to build a deeper understanding of the IR origins. Comparing fingerprints is natural, but stars are even more talkative than fingers. A fingerprint reveals a person's identity, but not their age or mood or habits. Starlight, on the other hand, reveals almost everything. It tells us how hot the star is, how dense its outer layers are, how fast it is moving, how old it might be, and what kinds of processes are unfolding deep within. It is more like listening to a voice, one that can express tone, rhythm, accent, and emotion all at once. A star's spectrum carries the tone of its temperature, the rhythm of its vibrations, and the subtle hints of its magnetic activity. In that sense, each star has its own voice. This method of reading starlight, gentle though it is, forms the foundation of much of modern astronomy. Without it, we would have no clear way to understand what lies beyond our solar system. We could see stars, but we would not know what they are made of or how they change over time. Spectroscopy turns distant points of light into complete stories. It transforms the night sky from a collection of dots into a library of stellar biographies. Perhaps the most calming part of all this is how quietly the universe shares its information. There is no need for probes to fly into distant stars or for dangerous experiments in deep space. The stars simply shine, and their light, shaped by physics, carries everything with it. All we have to do is receive the light, spread it into its colors, and listen to the patterns that appear. In this way, stars talk across enormous distances, and astronomy becomes an act of patient listening. So the next time you glance upward and see a star twinkling softly, remember that it is not silent. It is sending out a message encoded in its light, a message that has traveled far across the void to reach you. If we know how to interpret that message, we can learn almost everything about the distant world it came from. In a universe filled with darkness, Stars communicate through light, and through that light, they tell us who they are. Once a star settles into the long, steady rhythm of its life, something remarkable happens. After all the turbulence of its birth, the swirling collapse of its cloud, the formation of its core, and the quiet ignition of fusion, the star finally enters a stage of profound stability. This is called the main sequence, a phase so calm and enduring that it accounts for most of the star's existence. If a star's entire lifetime were compared to a human life, the main sequence phase would be the long, peaceful middle decades where growth has finished, decline has not yet begun, and the days flow by with a comforting regularity. During this time, the star shines with a steady light, powered by the fusion of hydrogen into helium at its core. The rate of fusion is not frantic, it is measured and balanced, producing just enough energy to counter the inward pull of gravity. From the outside, nothing appears to change. A star can look nearly identical for billions of years, glowing with the same brightness and color while the galaxies drift around it. But inside, the star is engaged in continuous delicate work. Every moment, hydrogen nuclei are merging in the core, releasing energy that moves outward in a slow migration, eventually emerging as starlight. The pace of this transformation depends heavily on the star's mass. A small star, like a red dwarf, fuses hydrogen at an exceptionally slow rate. Its gravity is gentle, and the pressure in its core is modest, so the fusion reactions proceed quietly. This means a red dwarf can live for trillions of years, far longer than the current age of the universe. In fact, no red dwarf is old enough yet to have reached the end of its life. They burn so efficiently and so patiently that they are expected to outlive every other kind of star, becoming the last luminous objects in a far future cosmos. They are the quiet, enduring beacons of the universe. A star like the Sun with a moderate mass burns hydrogen faster. It shines steadily for around 10 billion years, spending a long middle portion of that time in a near-perfect state of balance. These stars are neither hurried nor leisurely in their fuel use. They sit comfortably between extremes, shining brightly enough to warm nearby planets without exhausting themselves too rapidly. The Sun is a perfect example of this balance. It is old enough that it has already spent billions of years in the main sequence, yet young enough that it still has billions more to go. Large stars, meanwhile, live fast and luminous lives. Their enormous gravity creates immense pressure in the core, forcing hydrogen to fuse at a rapid rate. As a result, they produce incredible amounts of energy and shine with brilliant blue or blue-white light. But this brilliance comes at a cost. These stars burn through their hydrogen quickly, living for only a few million years before they begin to change dramatically. To a star, size is destiny. The more massive it is, the shorter and more intense its lifespan will be. Even though main sequence stars appear unchanging from afar, gentle adjustments are always happening inside them. As hydrogen is steadily converted into helium, the core's composition slowly shifts. Helium, being heavier, settles toward the center, increasing the core's density. This changes the balance of pressure and temperature in subtle ways. Over millions and billions of years, the core gradually contracts slightly under the increasing weight of helium. As it contracts, the temperature rises. This slow warming increases the fusion rate, which in turn causes the star to brighten ever so slightly. These changes are gradual and unfold across vast time scales. No observer would notice the change across an ordinary lifetime. Even entire civilizations would live and fall without detecting a difference. But across geological ages, the change becomes meaningful. For stars like the Sun, the brightness has increased since their earliest days, and it will continue to rise gently as the core evolves. Stars may appear serene, but within them a quiet evolution is always underway. In addition to the core changes, the star's outer layers also adjust in subtle ways. As energy P reduction increases, the layers expand slightly. The star's size and brightness respond to the internal shifts, maintaining equilibrium between gravity pulling inward and the outward pressure created by fusion. This is not a fragile balance, it is remarkably self-regulating. If energy production momentarily rises, the increased pressure will cause the star to expand, which cools the core slightly and slows the reaction rate. If production drops, gravity allows the core to contract, heating it up again. In this way, stars naturally stabilize themselves, resisting both collapse and runaway expansion. These self-correcting mechanisms are one reason the main sequence phase feels so calm. Stars are incredibly resilient during this part of their lives. They have settled into a comfortable pattern where their internal forces are matched, their temperatures are steady, and their energy output is reliable. It is this long stretch of stability that makes life on nearby planets possible. A star that flickered wildly or changed temperature rapidly would create an unstable environment. But main sequence stars are steady companions, offering light and warmth across immense periods. As helium accumulates in the core, this peaceful stability slowly edges toward transformation. The star is constantly preparing for the next stage. Even though it may be billions of years away, the increasing helium content changes the star's internal structure in ways too subtle to see, but too important to ignore. Eventually, the core will become dominated by helium, and the star will no longer be able to fuse hydrogen in that region. The fusion will shift outward into surrounding layers, and the star will begin its slow departure from the main sequence. But for now, during this long middle stretch, the star shines with a quiet confidence. It is worth noting that most stars spend around 90% of their lives in this stable phase. That means if you look at a random star in the sky, the odds are overwhelming that it is in the main sequence. The dramatic moments, the collapse, the explosive endings, the strange remnants are brief compared to the long, patient glow of the middle years. Stars are not defined by their dramatic beginnings or their spectacular endings. They are defined by the vast, tranquil expanse of time, in which they simply shine. In this sense, the main sequence is the true life of a star. It is a time of stability, quiet adjustment, and gentle evolution. It is where stars spend most of their existence, illuminating the universe not with bursts of energy but with a steady, enduring light. And as that light travels across space, it carries with it the long history of a star that has been shining patiently and reliably for billions upon billions of years. The quiet consistency of the main sequence is the very foundation of cosmic rhythm. When a star has spent billions of years quietly fusing hydrogen in its core, a slow but inevitable change begins to unfold. Hydrogen is not used up in the entire star all at once. Instead, the transformation occurs at the very center, where temperatures and pressures are highest. Over countless ages, the core gradually fills with helium, the ash of fusion, until eventually the hydrogen supply in this central region becomes too thin to sustain the reactions that once powered the star so reliably. This is not a sudden moment, not a dramatic switch turning off, but a long drifting toward a new phase of life. The star does not immediately dim or falter. Instead, it begins a graceful, complex transformation shaped by the physics of pressure, heat, and gravity. With hydrogen fusion slowing down at the center, the delicate balance that has held the star steady begins to shift. Gravity, which has always tried to pull the star inward, now finds less resistance from the declining energy output of the core. As a result, the core starts to contract. This contraction is not a collapse, but a steady tightening, like drawing in a loose thread. As the core shrinks, the temperature rises because gravity is compressing the gas into an even denser and hotter state. This temperature rise sets the stage for new changes in the layers surrounding the core. Even though hydrogen fusion cannot continue in the center, there is still plenty of hydrogen in the region just above it. As the contracting core heats up the surrounding layers, the temperature becomes high enough to ignite hydrogen fusion in this outer shell. Fusion begins again, not in the very heart of the star, but in a growing ring around the helium core. This shell burns hotter than the original core ever did, because it is experiencing the combined effects of gravitational compression and increased temperature. The energy generated in this shell flows outward, exerting tremendous pressure on the star's outer layers and causing them to expand dramatically. As the outer layers swell, the star grows to enormous proportions. A star that was once modest in size becomes a red giant, and if it is massive enough, it can grow into a red supergiant. These stars can reach sizes so vast that if the Sun were to expand in this way, it would engulf the inner planets and stretch far beyond the orbit of Earth. Despite their enormous size, red giants have relatively cool surfaces, which is why they shine with a warm reddish hue. The surface temperature drop comes from the expansion itself. When the outer layers stretch outward, they cool, much like air cools when it expands in Earth's atmosphere. This change in surface temperature might make the star look dimmer. But interestingly, the opposite is often true. Even though the surface cools, the sheer size O. The expanded star means that it emits far more light overall. It becomes brighter, sometimes hundreds or thousands of times brighter than it was during its long main sequence life. This is one of many counterintuitive delights in stellar physics. A cooler star can shine more brightly simply because its surface area has grown so vast. It is as if the star has traded a focused, intense glow for a softer but much more extensive radiance. Inside the star, the structure is becoming more complex. The contracting core, now composed mainly of helium, continues to heat up. If the star is massive enough, the core eventually becomes hot enough to begin fusing helium into heavier elements such as carbon and oxygen. This begins in a sudden and dramatic ignition known as the helium flash for stars of moderate mass. Though the event is contained entirely within the stellar interior, for larger stars, helium fusion begins smoothly, without a sudden burst, because their cores are not as tightly compressed. In either case, the onset of helium fusion marks another shift in the star's internal balance. As helium burns in the core, hydrogen continues to burn in the shell surrounding it. The star becomes layered, with each region supporting a different kind of fusion. The outermost layers remain enormous and cool, giving the star its red giant appearance. Below that, hydrogen fuses in a hot shell, adding more helium to the core. Deeper still, helium fuses into heavier elements. The result is a star that has become stratified, with shells nested inside one another like the layers of a cosmic onion. Each layer contributes to the energy output, and each responds differently to changes in temperature and pressure. These layers can create instability. The star can pulse, expand, and contract over long cycles. Some red giants grow brighter and dimmer in rhythmic patterns, their outer envelopes, acting like vast, breathing atmospheres. Small changes in the fusion shells can send ripples through the star, altering its brightness or size in gentle oscillations. These pulsations are slow, unfolding over months or years, but they reveal the restless inner workings of a star that has left behind the steady calm of the main sequence. As all this unfolds, the star's outer layers become loosely bound. The expansion makes them less tightly held by gravity, and the increasing internal movements can push material outward into space. Over time, the star may lose a significant portion of its mass through stellar winds, creating clouds of gas and dust that drift into the surrounding space. These materials can eventually become part of new stars, planets, or nebulae, continuing the cosmic cycle. The transition from a stable main sequence star to a red giant is one of the most dramatic transformations in a star's life. But it is not a violent upheaval. It is a slow evolution shaped by the same forces that guided the star from the moment of its birth. Gravity compresses the core, heat rises, outer layers respond, and new fusion processes take over. The star adapts to its changing fuel supply, adjusting its structure in a way that maintains balance for as long as possible. This phase marks the beginning of the end, but it is also a period of remarkable beauty and complexity. Red giants and supergiants are among the most luminous objects in the sky, glowing with a warm, soft light that belies the intense activity occurring within. Their expanded envelopes shimmer with convection, pulsation, and waves. Their cores burn with new forms of fusion, forging elements that will enrich the galaxy long after the star itself has faded. A star growing old is not fading into irrelevance. It is entering a grand transformative stage, reshaping itself from the inside out. The gentle decline of hydrogen in the core sets off a chain of changes that alter the star's size, color, brightness, and internal structure. And through all these changes, the star remains governed by the same elegant balance between gravity and pressure that guided it through its long middle years. In this way, the aging of a star is not simply a descent toward its final moments. It is a period of expansion, renewal, and deeper complexity, revealing layers of structure and behavior that were hidden during its youth. Even in its later years, a star continues to shine, telling the universe that its story is not yet over. When a small or medium-mass star reaches the end of its long and peaceful time as a red giant, its final chapters begin with a slow unraveling rather than an abrupt collapse. These stars have lived patient, steady lives, fusing hydrogen into helium for billions of years before using up the fuel that once kept their cores in perfect balance. Now, with hydrogen fusion having shifted to surrounding shells and helium fusion working within the core, the star enters a period marked by instability, pulsing brightness, and a gradual release of its outer layers. These final moments are not violent. They are almost gentle, like the slow exhale of a luminous being preparing to return its material to the galaxy. As the helium-burning core becomes heavier and denser, the outer layers become more loosely bound. They no longer cling tightly to the star. Instead, they begin to drift outward, pushed by radiation and stirred by turbulent motions beneath the surface. Red giants often swell to enormous sizes during this phase, and with their extended atmospheres come large, slow pulsations. These pulsations cause the star to brighten and dim over repeating cycles, sometimes over many months or years. Each pulse can send material drifting off into space, forming dusty shells or delicate plumes around the aging star. Over time, these losses accumulate. A red giant can shed a significant fraction of its mass through these repeated pulsations and gentle stellar winds. The star is not exploding. It is peeling away layer after layer, sending its outer material into the darkness in a quiet display that is both beautiful and essential for the cosmic cycle of matter. Some of the elements in these layers, such as carbon and nitrogen, were created during the star's own nuclear processes and are now returning to the interstellar medium, ready to become part of new stars, planets, and perhaps even the seeds of life. Eventually, the shedding of material reaches a threshold where the red giant loses most of its envelope, leaving behind a smaller, denser core surrounded by an expanding cloud of glowing gas. This glowing cloud is called a planetary nebula. This name has nothing to do with planets, but instead comes from early astronomers who thought these objects resembled planetary disks through their small telescopes. Despite the misleading name, planetary nebulae are among the most visually striking structures in the universe. They form intricate shapes, rings, bubbles, spirals, and filaments, depending on the star's rotation, magnetic fields, and the motions of the gas being expelled. The colors of a planetary nebula come from the way different elements respond to the intense ultraviolet radiation emitted by the hot, exposed core. Hydrogen glows with a soft red, oxygen shines with a delicate blue-green, and nitrogen contributes warm pink hues. These glowing shells expand outward over tens of thousands of years, creating luminous sculptures in space that can stretch across light years. For a brief period in astronomical terms, the star that once shone steadily for billions of years becomes the centerpiece of a cosmic lantern, illuminating its own remains in a final gesture of beauty. At the center of the planetary nebula lies the remnant core, now transformed into a white dwarf. White dwarfs are extraordinary objects. They are roughly the size of Earth, but contain a mass comparable to that of the Sun. This incredible density means a teaspoon of white dwarf material would weigh many tons. The reason for this density is that the star can no longer support itself through fusion. Instead, it is held up by electron degeneracy pressure, a quantum mechanical effect arising from the behavior of electrons when matter is compressed to extreme levels. It is not fusion that keeps a white dwarf stable, but the laws of physics at the smallest scales resisting further collapse. A newly formed white dwarf is unimaginably hot, glowing with temperatures that can exceed 100,000 degrees at its surface. Yet, it has no internal source of heat. There is no fusion at its core. Instead, the white dwarf shines because it is slowly radiating away the leftover heat from its earlier life stages. This cooling process takes an astonishing amount of time. White dwarfs fade at a glacial pace, gradually dimming as they release their stored energy into space. In the first billion years or so, the white dwarf cools enough to change from a blue-white color to a softer yellow or red. Over many billions more, it grows dimmer, eventually becoming so faint that it can no longer be seen with ordinary telescopes. But even then, the process is not finished. A white dwarf is so dense and so well insulated that it takes trillions of years to lose all its residual heat. That is far longer than the current age of the universe, which means no white dwarf has yet completed this cooling journey. Every white dwarf in existence is still glowing. Theoretical models suggest that after an astonishing amount of time, longer than any time scale humans can intuitively grasp, a white dwarf will eventually cool to the point where it no longer emits any visible light. It would become a cold, dark object known as a black dwarf. This term describes not a star that has collapsed or exploded, but one that has simply run out of energy to shine. A black dwarf would be a husk of carbon and oxygen, crystallized and cold, drifting silently through a universe that may itself be approaching a state of deep stillness. However, no black dwarfs exist yet because the universe is still too young. It would take many trillions of years for even the oldest white dwarfs to cool enough to reach this hypothetical state. In a way, white dwarfs represent a snapshot of the far future, quiet reminders that stars can persist long after their shining days have ended. This strange death of small stars is not a catastrophic ending, but a gentle progression. These stars do not collapse into neutron stars or black holes. They do not explode in a spectacular supernova. Instead, they age with a kind of cosmic grace. They shed their outer layers in shimmering veils, exposing their glowing cores. They cool slowly, drifting through trillions of years until they become dim, silent relics of a universe long past its prime. And yet, in their quiet way, they have an enormous impact. The material they release into space becomes part of new stars and planets. The carbon in your body may have once been part of a red giant's final breath. The oxygen you breathe could have been forged in the core of a star that gently released it into space as it died. These small stars, humble though they seem, are among the great recyclers of the cosmos, seeding the galaxy with the ingredients needed for new beginnings. Their death is not an ending so much as a transition. A red giant becomes a planetary nebula becomes a white dwarf slowly cools until it becomes a silent dark ember. Through each stage, the star transforms, contributing to the ongoing story of the universe. Even in their final moments, small stars continue to shape the cosmos in subtle but profound ways. When a massive star reaches the end of its long middle years, the story of its aging takes a very different path from the gentle drifting of smaller stars. These giants have spent their lives burning bright and fast, fusing hydrogen and then helium at enormous rates to support their immense weight. Their cores become hotter and denser with time, and unlike small or medium stars, their great mass allows them to continue fusing heavier and heavier elements once helium is gone. What follows is one of the most dramatic transformations in the universe, a sequence of changes that unfolds deep within the stellar core and ends in an explosive event so powerful that it can briefly outshine an entire galaxy. After a massive star finishes fusing helium, it begins to forge carbon in its core. As the temperature continues to rise, the star can fuse carbon into oxygen, neon, and other heavier elements. Each of these fusion processes requires even greater heat and pressure, conditions only massive stars can provide. The core becomes a kind of layered furnace with different fusion reactions happening in nested shells. Carbon burns in one region, oxygen in another, neon in another. Further out, hydrogen and helium may still be fusing in their own shells. The effect is a structure reminiscent of an onion, with each layer producing energy through a different nuclear reaction. These reactions proceed more quickly as the star runs out of lighter elements, creating a cascade of increasingly rapid fusion stages. As long as the star can fuse new elements to release energy, it can resist the pull of gravity. But this process has a limit. When the core begins to produce iron, the rules change. Iron represents a turning point in stellar fusion because fusing iron into heavier elements does not release energy. Instead, it consumes energy. This means the star can no longer use fusion to support itself. It has reached the end of the line. The iron in the core grows, accumulating from the fusion of lighter elements in the shell surrounding it, until the core becomes a heavy, inert mass that can no longer contribute to the outward pressure holding the star up. When the mass of the iron core becomes too great, gravity wins. The core collapses in a fraction of a second, imploding under its own weight with breathtaking speed. At this moment, the density increases so rapidly that atomic nuclei are crushed together. Electrons and protons merge into neutrons, and the core shrinks to an incredibly dense state, smaller than a city yet heavier than the sun. The collapse releases a shock wave, but initially the shock stalls as it pushes against the infalling material from the outer layers. For a brief moment, it appears the collapse will continue unchecked. However, something extraordinary happens deep within the star. As the core collapses, it releases an enormous flood of neutrinos. These tiny, nearly massless particles rarely interact with matter. Under normal circumstances, neutrinos pass through stars, planets, and people without leaving a trace. But during a massive star's collapse, the density of the core is so extreme that a small fraction of these neutrinos interact with the surrounding material. These interactions deposit energy into the infalling layers, helping to revive the stalled shockwave. In this way, neutrinos play a crucial role in powering the explosion that follows. The revived shockwave suddenly surges outward, racing through the star's outer layers. When it breaks free of the stellar surface, it releases a burst of light and energy so intense that the star becomes billions of times brighter than it was a moment before. This burst is a supernova, one of the most powerful events known in nature. For a short period, a single supernova can shine more brightly than an entire galaxy filled with hundreds of billions of stars. It is a moment of sudden brilliance that marks the end of the star's life. The explosion tears apart the star's outer layers, hurling heavy elements into space at incredible speeds. These elements include carbon, oxygen, silicon, magnesium, and even elements heavier than iron that were created in the final moments before the explosion. The universe relies on these giant stars to produce and spread the heavier elements essential for planets, oceans, living organisms, and the chemistry of life. Without supernovae, the periodic table would be a much poorer thing, and planets like Earth might never have formed. After the explosion, what remains of the star depends on its mass. If the original star was moderately massive, the collapsing core forms a neutron star, a dense, city-sized sphere composed almost entirely of neutrons. If the original star was truly enormous, far more massive than the Sun, the collapse continues beyond the neutron star stage. Gravity becomes so strong that not even neutron degeneracy pressure can resist it. The core collapses further, forming a black hole. Despite the dramatic nature of a supernova, the star does not die in vain. Its explosive end enriches the galaxy with the elements it forged over its lifetime. These elements drift through space, gathering into new clouds that may eventually form new stars and planets. Thus, the death of a giant star becomes a beginning for countless others. The calcium in your bones, the iron in your blood, the gold in jewelry, and many of the elements in Earth itself were once forged in the core of a massive star and thrown into space, be a supernova long before the Sun was born. The violent death of a giant star is both an ending and a contribution to the future. The core collapses. The explosion spreads heavy elements. Neutrinos carry away energy, and new worlds benefit from the debris left behind. Even in their most dramatic final moments, giant stars participate in the ongoing story of the universe, shaping galaxies and seeding the cosmos with the materials needed for new generations of stars and planets. Their end may be violent, but it is not meaningless. It is a crucial chapter in the cosmic cycle, one that ensures that the universe remains rich, diverse, and full of possibility. When a massive star ends its life in a spectacular supernova, the outward explosion is only half the story. What remains behind in many cases is an object so dense, so compact, and so utterly strange that it defies ordinary imagination. This remnant is a neutron star, one of the most extreme forms of matter in the universe. From the outside, a neutron star might look small and unassuming, only about the size of a city, but appearances can be misleading. A neutron star is a universe of weirdness contained in a sphere no bigger than a town, and every aspect of its structure pushes the limits of what physics can comfortably describe. To appreciate how dense a neutron star really is, imagine taking the mass of the Sun and compressing it into a sphere roughly 20 kilometers across. That is smaller than many metropolitan areas. A teaspoon of neutron star material would weigh billions of tons. It would be so heavy that if you could somehow drop it onto Earth, it would fall straight through the crust and plunge toward the core without even slowing down. Trying to compare this to anything familiar is nearly impossible. But one gentle analogy is that the density of a neutron star is like cramming the entire human population into the volume of a sugar cube. The mind cannot easily hold that idea, which is part of what makes neutron stars so fascinating. But density is only the beginning of their strangeness. The structure of a neutron star is layered in a way that resembles nothing found on Earth. The outermost region is called the crust, a thin shell of incredibly dense matter composed of atomic nuclei, packed much closer together than in any ordinary solid. As you move inward, the crust gives way to a region where neutrons begin to drip out of these nuclei, forming a fluid mixed with the residual protons and electrons. Below that lies the outer core, a vast ocean of superfluid neutrons. This superfluid does not behave like ordinary liquid. It flows without friction, meaning that once it starts moving, it continues endlessly unless something interferes. Deeper still is the inner core, a region so dense that even the best theories struggle to describe it. Some models suggest the inner core contains a soup of quarks, the fundamental building blocks of protons and neutrons, freed from their usual confined state. Others propose exotic phases of matter made of particles that may not exist anywhere else in the universe. In a sense, the core of a neutron star is a laboratory for physics under conditions that cannot be recreated on Earth, conditions so extreme that the very nature of matter behaves differently. Neutron stars also possess magnetic fields of incredible strength. Earth's magnetic field is powerful enough to guide compasses and produce auroras. Yet, it is almost gentle compared to what neutron stars generate. A neutron star's magnetic field can be billions or even trillions of times stronger. If Earth had such a field, it would tear apart objects made of metal and strip atoms from their electrons. Some neutron stars, known as magnetars, push these magnetic fields to unbelievable extreme, so intense that they can distort the shapes of atoms themselves. Even the act of standing 100 kilometers away from a magnetar, assuming you had a way to survive everything else, would expose you to magnetic forces capable of rearranging matter at the molecular level. Among neutron stars, one category stands out for its remarkable behavior: pulsars. Pulsars are neutron stars that emit beams of radiation from their magnetic poles. Because these beams are not aligned with the star's rotation axis, they sweep through space like the beam of a lighthouse. Each time the beam crosses Earth, astronomers detect a pulse of radiation, giving pulsars their name. Some pulsars spin incredibly fast, rotating many times per second with perfect regularity. Their timing is so precise that they rival the accuracy of atomic clocks. It is a humbling thought that an object created in a violent stellar explosion can become one of the universe's most reliable timekeepers. Yet, despite their stability, neutron stars can behave unpredictably. One of their most intriguing behaviors involves sudden shifts in rotation, known as glitches. These glitches occur when the crust of the neutron star suddenly cracks or rearranges itself, sending a tiny jolt through the star's rotation. This is sometimes described as a starquake, a seismic event on an object far denser and stranger than any planet. The glitch causes the pulsar to momentarily speed up. Astronomers observe this as a sudden change in the timing of its pulses. After the glitch, the star gradually settles back into its previous rhythm. These events provide valuable clues about the structure of the crust and the behavior of superfluid matter inside. Starquakes are not the only oddities. Because the inner layers of a neutron star behave as a superfluid, they can rotate differently from the crust. This means the star is not a single sol. ID spinning body, but a combination of components rotating in slightly different ways. This differential rotation can lead to surprising interactions that influence the star's magnetic field or its spin. The result is an object constantly balancing competing forces in ways that challenge scientists to refine their understanding of how matter behaves under such extraordinary conditions. Neutron stars test physics at every level. Their densities challenge our understanding of the structure of matter. Their magnetic fields push the limits of what atoms can endure. Their superfluid interiors defy familiar intuition about how fluids should move. Their cores may contain forms of matter that cannot exist elsewhere. Every observation of a neutron star adds another piece to a puzzle that scientists are still trying to assemble, and each new discovery deepens the mystery rather than resolving it. Yet, for all their complexity, neutron stars are also elegant in their own way. They are the remnants of massive stars that once burned brightly, and their existence completes a cycle of stellar evolution. They serve as cosmic laboratories where the laws of physics are tested under conditions far beyond what humans can simulate. They reveal patterns of rotation and vibration that help astronomers measure distances, understand gravity, and explore the behavior of matter at its most extreme. Even their weirdness has a quiet logic. Gravity compresses matter until it becomes almost pure neutrons. Rotation accelerates to maintain balance. Magnetic fields strengthen as the star shrinks. Every property of a neutron star is connected to the basic rules of physics stretched to their limits. What emerges is an object that embodies both familiarity and strangeness. It is made of the same fundamental particles that compose everything else, yet assembled in a way that makes it utterly unique. Neuter. On stars remind us that the universe contains wonders far beyond everyday experience. They are relics of enormous stars compressed into forms that challenge imagination, glowing faintly as they spin, pulse, and quake in the darkness. Studying them is not just a scientific endeavor, but a humbling one, revealing how much of the universe lies outside the comfortable boundaries of intuition. A neutron star is a monument to extremes, a cosmic riddle, and a quiet beacon in the deep night. And even though their behavior can be baffling, their existence expands our understanding of what matter can do when pushed to its absolute limits. In a universe filled with familiar light from ordinary stars, neutron stars stand apart, humming with a weird, precise, and beautiful energy all their own. When a truly massive star reaches the end of its life, its final collapse can go beyond even the extraordinary density of a neutron star. If the remaining core is heavy enough, gravity overwhelms every possible force that might resist it. There is no pressure that can hold the material up, no arrangement of particles that can support the weight. The collapse continues inward until the star, as it once existed, is gone, replaced by something far stranger, a black hole. It is not a hole in the ordinary sense, nor a tunnel, nor a swirling drain. It is a place where matter has been compressed beyond any familiar form, leaving behind a region where gravity is so strong that nothing, not even light, can climb back out. A stellar mass black hole begins with this moment of collapse. The outer layers of the star are often blown away by the supernova, but the core falls inward, shrinking to an unimaginably small point. The remaining gravity becomes concentrated into a tiny region, curving space and time so severely that the structure of the universe itself bends around it. What is left is not a solid object with a surface. Instead, the boundary defining a black hole is known as the event horizon. This horizon is the point at which the pull of gravity becomes so strong that escape becomes impossible. If light cannot leave, no signal, sound, or information can return once it crosses this boundary. Yet the event horizon itself is not a physical barrier. If you were able to drift toward it, setting aside the many other things that would make this a very unhealthy decision, you would not feel a bump or a wall. Crossing it would feel no different than floating into deeper darkness. The event horizon is best imagined as a point of no return. It marks the distance at which the inward pull becomes absolute. Outside this boundary, objects can still orbit safely. They do not get sucked in, dragged in, or devoured. This is one of the biggest misconceptions about black holes. They do not roam the universe, swallowing everything in their path. A black hole has gravity, yes, but only as much gravity as the mass that formed it. If the Sun were magically transformed into a black hole of the same mass, Earth would continue to orbit in almost exactly the same way. The world would become cold and dark, but it would not be pulled inward. The idea that black holes behave like cosmic vacuum cleaners is more fiction than physics. However, black holes can influence their surroundings in dramatic ways when material falls toward them. If gas, dust, or even a wandering star gets too close, this material can begin to spiral inward. As it does, it forms a structure known as an accretion disk. The gas in the disk does not fall straight in, but circles around the black hole, gradually losing energy and spiraling closer. This motion generates tremendous friction within the disk, heating the material to extreme temperatures. When the gas becomes hot enough, it glows, often producing a bright energetic light in X-rays or ultraviolet wavelengths. The black hole itself remains invisible, but the glowing disk around it becomes a beacon that reveals the presence of something with a powerful gravitational pull at its center. Despite their reputation for stillness and silence, black holes can spin. In fact, many of them rotate at astonishing speeds. When the original star collapsed, it retained its angular momentum, meaning that any slight rotation the star had becomes amplified as its core shrinks. The same effect causes a figure skater to spin faster when pulling their arms inward. For a black hole, this means the rotation can become so rapid that space itself is dragged around with it. This phenomenon, known as frame dragging, is difficult to visualize, but can be understood gently as the black hole's rotation influencing the paths that objects must take around it. Even light must follow the twisting geometry created by this spin. Not all black holes have glowing accretion disks. Many are silent and solitary, drifting unnoticed through space. Since they emit no light, they cannot be seen directly. Yet, astronomers have become skilled at finding these invisible objects by observing the behavior of things around them. When a black hole orbits a companion star, the star's motion can reveal its unseen partner. If the star wobbles or speeds up and slows down in a regular pattern, it may be responding to the gravitational pull of a black hole. In other cases, gas from a nearby star may be drawn toward the black hole, forming a bright accretion disk that astronomers can detect. Even without visible light, a black hole can announce its presence through the motions of stars, the heating of gas, or the pattern of radiation escaping from the surrounding disk. There are also more indirect methods. When black holes merge, the ripples they create in space, known as gravitational waves, can be detected by sensitive instruments on Earth. These waves carry information about the masses and spins of the black holes involved, allowing astronomers to identify systems that were once completely hidden from view. Even lack of light can be a clue. If a region of space contains a bright star circling an unseen mass, and that mass is too heavy and too compact to be a neutron star, then a black hole becomes the simplest explanation. Perhaps the most captivating thing about black holes is how they reinterpret the idea of a star. In a sense, a black hole is a star turned inside out. The core collapses until it becomes a singular region of infinite density, at least according to current theories, and the structure that once scattered light into the universe becomes instead a region from which light cannot escape. What was once an object made of fiery plasma becomes a gravitational well surrounded by warped space-time. Yet even in this strange state, black holes remain connected to their origins. They are not mysteries disconnected from the rules of physics, but natural, expected consequences of gravity acting on enough mass. Despite this, black holes still challenge understanding. Their extreme environments push theories to their limits. What happens in the center remains unknown. The behavior of matter near the event horizon is still being studied, and the way black holes interact with quantum physics is an open question that continues to intrigue scientists. They are familiar in one sense, born from stars shaped by gravity, yet alien in another, revealing the limits of what is known and the possibilities that remain hidden. Black holes are not holes in the emptiness of space. They are remnants of brilliant stars that once illuminated the galaxy, now transformed into regions that reshape the very fabric of the cosmos. They do not shine on their own, yet they influence everything near them. They do not call attention to themselves, yet they are among the most powerful objects ever discovered. And when astronomers detect the faint tug they exert on a companion star, or the swirling glow of an accretion disk, or the trembling of space-time from a distant merger, they are reminded that even the darkest places in the universe have stories to tell, stories rooted in stars' lives and deaths. When imagining a star, many people picture a single shining sphere drifting alone through the galaxy, much like the sun sits at the heart of the solar system. But in the wider universe, solitude is not the norm. Most stars are born with at least one companion, creating pairs or even whole families that orbit around shared centers of gravity. Binary stars, despite appearing exotic in stories or science fiction, are actually wonderfully ordinary. They are the quiet workhorses of the galaxy, engaged in gravitational dances that can last for billions of years. Their interactions shape their evolution in ways that single stars never experience, making binary systems some of the most intriguing theaters of stellar behavior. At first glance, the idea of two stars orbiting each other might sound chaotic. After all, stars are massive objects with strong gravitational pulls, yet their motion is serene and orderly. If you were watching from afar, you would see the two stars orbiting a point in space known as their center of mass. The center of mass acts as the gravitational balance point between them. Each star traces out its own orbit around this point, neither dominating entirely nor drifting freely. Their orbits can be nearly circular, sweeping gracefully around the center, or elongated, stretching into long ovals, depending on how they formed. Regardless of shape, the system moves with surprising stability, like two dancers in a slow waltz, each on guided by the other's presence. Binary stars can come in many varieties. Some pairs contain two stars very similar in mass and brightness, evolving side by side like twins. Others pair stars of different masses, with one star evolving more quickly while the other lingers in earlier stages of its life. There are also systems where one member has already died and become a white dwarf, a neutron star, or even a black hole. The diversity of these pairings creates a wide range of behaviors. In some cases, the stars orbit far apart and barely influence one another. In others, the stars orbit so closely that their histories become deeply intertwined, altering each other's fates in profound ways. One of the most interesting aspects of binary stars is their mass transfer potential. This occurs when one of the stars expands during its giant phase and grows large enough to spill material toward its companion. The gravitational pull of the other star can capture some of this drifting gas, effectively siphoning mass from its partner. This process can dramatically change the course of evolution for both stars. The star losing mass may become smaller, cooler, or evolve more quickly toward its final stages, while the star gaining mass may grow hotter and more luminous. Mass transfer is like a slow exchange of identity, where each star gradually reshapes itself as it gains or loses material. In some extreme cases, the stars orbit so closely that they share a single atmosphere. These are known as contact binaries. Instead of being two separate stars with distinct surfaces, they resemble a double-lobed shape connected by a common layer of gas. The stars inside this shared envelope exchange material freely, constantly reshaping one another. Their orbit brings them so near that their outer layers touch, creating a system more united than separate. This configuration is rare and delicate, and it often leads to instability. Over time, the two stars may spiral closer together, eventually merging into a single or massive star that shines with renewed brightness. When mergers occur, the results can be spectacular. A stellar merger can produce a sudden brightening known as a luminous red nova, where the combined star flares into visibility before settling into its new form. These events are not as powerful as supernovae, but they are still dramatic, releasing enough energy to be seen across great distances. After the merger, the newly formed star may behave differently from either of its predecessors, possessing a mix of internal structures and compositions inherited from both. In a sense, binary systems allow stars to reinvent themselves mid-life, or even after one partner has already died. Binary systems with dead stars also create unusual phenomena. For example, when a white dwarf orbits a companion that is still burning hydrogen, The white dwarf can steal material from the companion's outer layers. If enough material accumulates on the white dwarf's surface, it can ignite in a sudden burst known as a nova. Unlike a supernova, a nova does not destroy the star. Instead, it releases a bright but brief eruption of light before fading again. This cycle can repeat many times, creating periodic flares as the white dwarf continues to gather and ignite fresh material. In more extreme cases, if the white dwarf gathers too much mass from its companion, it can cross a critical threshold and collapse in a thermonuclear supernova. This type of explosion, known as a type Ia supernova, is so consistent in brightness that astronomers use it as a cosmic measuring tool to gauge the distances of faraway galaxies. Remarkably, these stellar explosions begin as gentle mass transfers between two stars quietly orbiting one another. The universe's most important distance, Ma. Archaeas arise from the intimate interactions within binary families. Binary systems containing neutron stars or black holes can create equally extraordinary outcomes. If a neutron star orbits a larger companion, it may siphon material from the companion's outer layers, forming a glowing accretion disk, much like those around black holes. In some cases, neutron stars in binary systems can emit powerful bursts of X-rays as matter crashes onto their dense surfaces. These X-ray binaries provide clues to the nature of extreme gravity and matter under intense pressure. Even binary systems composed of two living stars can end in unique ways. When both stars evolve into giants, their expanding envelopes may interact, creating complex shapes and flows of material. Some planetary nebulae, the glowing shells created when stars like the Sun shed their outer layers, show intricate patterns that can only be explained by the gravitational influence of a companion star. Spirals, rings, and hourglass shapes form because of the subtle gravitational tug of a nearby partner. These structures become beautiful final signatures of binary interactions. Binary stars illustrate how companionship changes everything. A single star's life follows a predictable path shaped mainly by its mass. A binary star's life, by contrast, can twist and transform depending on how the pair interact. Their gravitational dance, their exchanges of mass, their shared atmospheres, and even their dramatic endings reveal that the universe is not solely composed of isolated objects. Much of its richness arises from the relationships between stars, the ways they influence each other, and the surprising paths they take as they orbit together. In the end, binary systems remind us that stars are not always solitary wanderers. Many live in families, shaping each other's destinies over billions of years. Their gravitational bow NDS allow them to share matter, merge, or simply orbit peacefully. Each star acknowledges the other's presence in a dance choreographed by gravity itself. These stellar families show that the universe is filled with connections. Even in the vast emptiness of space, stars often find companions, and their lives become richer, stranger, and more beautiful because of it. Stars may all shine with a familiar glow, but their lives, personalities, and behaviors differ dramatically depending on one simple property: their mass. Mass shapes everything a star will ever be, from its color to its lifespan to the final form it takes at the end of its journey. Some stars live fast and bright, burning through their fuel in the cosmic equivalent of a sprint. Others glow softly for trillions of years, barely changing across spans of time so enormous that human imagination strains to grasp them. Between these extremes lies a whole family of stars, each following a path set by the amount of material gathered during its birth. At the smallest end of the stellar spectrum are red dwarfs, the most common type of star in the universe. They are tiny compared to the Sun, containing only a fraction of its mass. But their size belies their importance. Red dwarfs shine with a cool, dim light, often not much brighter than a strong incandescent bulb when viewed from a great distance. Yet, their faintness is a sign of stability. Because they are so small, their cores operate at relatively low temperatures and pressures. This means they burn hydrogen at an extraordinarily slow rate. While a large star rushes through its fuel, a red dwarf sips delicately, conserving its hydrogen with remarkable patience. This slow burning makes red dwarfs incredibly long-lived. While a star like the Sun will shine for around 10 billion years, a red dwarf can remain on the main sequence for trillions of years. The univ. RSE itself is not old enough for any red dwarf to have completed its main sequence of life. Every red dwarf ever born is still out there, quietly glowing and going about its work. Their steadiness makes them fascinating, but they also come with quirks. Some red dwarfs exhibit flares and bursts of activity, sending energetic particles into space. These flares, while small compared to the output of larger stars, can still affect nearby planets. Despite this, red dwarfs remain the turtles of the stellar world, slow, steady, and built for longevity. Moving up in mass brings us to stars like the Sun, moderate, balanced, and wonderfully predictable. Yellow stars occupy the middle ground of stellar evolution. They are hot enough to shine brightly, but not so hot that they burn through their fuel too quickly. Their surface temperatures produce white or pale yellow light, and their lifespans span billions of years. The Sun, for example, is roughly halfway through its long life, a comfortable middle-aged star enjoying the quiet stability that comes from balanced fusion reactions in its core. These yellow stars are ideal engines for planetary systems. Their light is strong enough to warm planets at comfortable distances, but not so intense that they scorch everything nearby. They evolve gently, giving planets plenty of time to form, cool, and potentially host life. A star like the Sun offers a kind of cosmic hospitality, creating conditions that endure long enough for chemistry to experiment and for complex systems to develop. This is part of what makes medium-mass stars so important in discussions about habitable worlds, offering stability across the slow passage of geological time. Above these moderate stars are the blue giants, the heavyweights of the stellar population. These stars are massive, often tens of times the mass of the Sun, and with great mass comes great heat. Air cores reach astonishing temperatures, allowing them to fuse hydrogen at a furious rate. This immense fusion output gives blue giants their brilliant color and luminosity. They shine so brightly that they can light up entire regions of space, casting their glow across nebulae and illuminating star-forming regions. However, their brilliance comes at a price. Blue giants live short lives, sometimes only a few million years. They burn their fuel so intensely that they quickly exhaust the hydrogen in their cores. Once this happens, they undergo a series of rapid transformations that eventually lead to spectacular deaths, supernovae that scatter heavy elements across the galaxy. Blue giants are the sprinters of the cosmic world, dazzling but brief. They contribute more to the universe in death than in life, forging the elements that later become parts of planets, oceans, and living creatures. Between stars and planets lies a class of objects known as brown dwarfs. They form much like stars, condensing from clouds of gas, but they never reach the critical mass needed to ignite sustained hydrogen fusion in their cores. They are sometimes called failed stars, though the term feels unkind. Brown dwarfs are interesting in their own right. They generate some heat through gravitational compression and limited fusion of deuterium, an isotope of hydrogen, but never become true stars. They glow faintly in infrared light, invisible to the naked eye, but detectable by telescopes designed to sense heat. Brown dwarfs represent the threshold between starlight and planet light, providing a link between the two realms. Across this spectrum, mass dictates everything. A small mass means a small core, low temperatures, and a slow, steady life. A moderate mass creates balanced conditions, allowing for long main sequence stability and gentle evolution. A large mass produces enormous pressures and temperatures, leading to high fusion rates, short lifespans, and dramatic endings. Even brown dwarfs follow this rule. Too little mass means no sustained fusion at all. Mass determines a star's brightness by controlling how fast fusion occurs. It determines temperature, with more massive stars glowing blue-hot and smaller ones shining in soft reds. It shapes lifespans, compressing the life of a blue giant into a fraction of the time a red dwarf enjoys. And it influences the path of evolution, from the slow and steady contraction of a tiny star to the explosive demise of a massive supergiant. It is comforting in a way that such variety arises from a single parameter. The universe does not need a long list of instructions to create its stellar diversity. It only needs the simple rule that gravity and pressure respond to mass. From that one principle, an entire gallery of stars emerges, each with its own behavior and destiny. Red dwarfs with their quiet persistence, yellow stars with their balanced warmth, blue giants with their bold, short-lived radiance, brown dwarfs sitting delicately on the boundary between glowing and not quite glowing. All of them are expressions of the same physics, shaped by the same laws, yet offering an incredible range of forms and lifetimes. In this way, the universe provides a gentle reminder that complexity often arises from simplicity. A single measure, mass, creates a rich tapestry of stellar lives. From the tiniest ember-like stars to the largest, brightest beacons in the sky. And as these stars evolve and eventually die, they pass their materials back into space, where new stars can form. Each generation carries the imprint of the masses that shaped them, continuing the cycle in an endless cosmic rhythm. Stars, whether giant, tiny, or somewhere in between, are all part of this grand story. Each one writes its chapter through the quiet burning of its core, the glow of its light, and the way its mass guides its life from beginning to end. In the vastness of the universe, this simple relationship creates an astonishing diversity, reminding us that even the stars follow a path written by their origins. Long before planets existed, long before oceans formed or life began to stir, the universe consisted mostly of hydrogen and a smaller amount of helium. These simple elements filled the early cosmos, drifting quietly through space until gravity gathered them into the first stars. What happened next changed everything. Stars became the universe's earliest chemists, forging new elements deep in their cores through the quiet and patient work of fusion. Every heavier atom that now exists, the carbon in forests, the oxygen in air, the calcium in bones, the iron in blood, was created inside a star or released in the moment of its death. Stars are not just light sources, they are factories of matter, shaping the ingredients needed for planets and life. The process that creates new elements is called nucleosynthesis. A long word for a simple idea, building heavier atoms from lighter ones. Inside a star's core, intense heat and pressure allow hydrogen to fuse into helium. Once a star ages and its core gets hotter, helium can fuse into carbon and oxygen. These reactions release energy, allowing the star to shine, while slowly rearranging the building blocks of the universe. The elements that power chemistry, biology, and geology were once the glowing products of stellar reactors. But this process only goes so far during a star's normal life. Fusion reactions inside stars can create elements up to iron. Iron is a kind of cosmic stopping point because fusing it does not release energy. Instead, it consumes energy. So once a star begins to accumulate too much iron in its core, no further fusion can occur there. For massive stars, this sets the stage for a dramatic finale. The star collapses and explodes in a supernova, an event powerful enough to forge many of the heavier elements found on the periodic table. Gold, silver, uranium, and dozens of other elements are created in the incredible heat of these explosions. During a supernova, the collapsing core releases an enormous wave of energy and particles. These particles collide with atoms in the outer layers of the star, adding neutrons and transforming them into heavier and heavier elements. In only a few seconds, the star manufactures a whole suite of new atoms. Then the explosion scatters these elements across space, enriching the surrounding regions with the materials needed to form new stars and planets. The universe's heaviest elements owe their existence to this brief and spectacular moment. A moment that happens only when a massive star reaches the end of its life. In recent years, astronomers have discovered another remarkable source of heavy elements: collisions between neutron stars. When two neutron stars spiral and merge, the violence of the event is almost unimaginable. These collisions release gravitational waves that ripple across space and produce extreme conditions, allowing new elements to form through rapid additions of neutrons. Some of the gold and platinum on Earth may have originated not from a supernova, but from such a collision billions of years ago. It is a strange and beautiful thought that the rings people wear, or the circuitry inside electronics, can trace their origins to the moment two collapsed stars collided in the deep past. Once these elements are created, they drift outward into interstellar space. Over time, they mix with dust and gas, forming clouds enriched by the ashes of long-dead stars. When new stars form inside these clouds, the planets around them inherit this enriched material. Every rocky planet is built from elements forged in earlier generations of stars. Water, too, owes its existence to stellar alchemy. The hydrogen in water comes from the early universe, but the oxygen was made inside stars long before any oceans formed. The periodic table, which looks like a neat grid of boxes, is really a record of stellar processes. Hydrogen and helium come from the beginning of the universe. Carbon, oxygen, nitrogen, and other vital elements were created in the life cycles of ordinary stars. Iron and elements near it on the table were built in the cores of massive stars and released through their explosive deaths. The heaviest elements were shaped in moments of extreme energy, supernovae and neutron star mergers, before being scattered across space. Because of this, the atoms in your body carry a history that stretches back billions of years. The carbon in your cells was once part of a star's core. The calcium in your bones was formed in the expanding shell of a dying giant star. The iron in your blood came from the core of a massive star that exploded long before the sun was born. Even the oxygen you breathe was created in stars that lived their entire lives and died before Earth existed. The universe recycled their materials, shaping them into new worlds and new forms of life. This connection is not poetic exaggeration. It is a statement of fact. You are literally made of star-created atoms. Every breath, every movement, every thought depends on elements produced by stars that lived and died billions of years ago. The atoms composing your body have traveled across unimaginable distances and timescales. They have been part of ancient stars, drifting nebulae, newborn solar systems, and finally the living organisms that walk on Earth today. In this way, life is the universe's way of reassembling its own material into something that can wonder about its origins. Stars, through their quiet fusion and their dramatic deaths, act as the cosmos's chemical engines. They take simple atoms and transform them into the diversity of matter found throughout the universe. They seed galaxies with the ingredients for planets, atmospheres, oceans, and living creatures. Their work spans billions of years, and the results persist long after the stars themselves have faded. When you look at the night sky and see the faint, distant glow of stars, you are seeing more than light. You are seeing the machinery of cosmic chemistry in action. You are watching the places where the atoms of future worlds are being made. And when you reflect on the fact that those very same processes created the material that forms your own body, the connection becomes humbling and astonishing. Stars do not only illuminate the universe, they construct it. They shape its chemistry, enrich its dust, and prepare the raw materials for new generations of stars and planets through their long lives and dramatic deaths. They ensure that space remains a place of endless possibility, and through the atoms they produce, they bind every living being to the history of the universe itself. The quiet work of cosmic recycling is a constant, gentle reminder that everything is interconnected. Galaxies may look serene from a great distance, like vast islands of soft light floating in darkness, but each one is shaped and sculpted by the stars within it. Stars are not just ornaments shining along the edges of spiral arms. They help build the structure of galaxies, illuminate their shapes, and guide their evolution across billions of years. When you look at a galaxy, every curve, every glow, every pattern of brightness is a quiet record of how its stars were born, how they lived, and how they interact with the gravity that binds them all together. In spiral galaxies such as the Milky Way, the most striking feature is the set of sweeping arms that wind outward from the center like luminous trails. These arms are not solid objects. They are regions where star formation is aspect, highly active. Gas and dust clouds drifting through the spiral pattern become compressed as they encounter waves of density in the rotating galaxy. This compression triggers the birth of new stars. Young, massive stars shine intensely blue-white, casting a bright glow that outlines the spiral arms and makes them visible even from tremendous distances. These bright stars burn hot and fast, living only a few million years. They illuminate the arms for a brief moment in cosmic time, before ending in supernovae that enrich the surrounding gas. But their short lives are enough to trace out the spiral structure like glowing brush strokes on a canvas. As these massive stars die, new ones form behind them, maintaining the luminous shape of the spiral arms. Without this ongoing cycle of star birth, spiral galaxies would lose much of their definition and fade into less distinct forms. Beyond the spiral arms lie clusters of stars that also shape galactic evolution. Young star clusters form in the densest parts of gas clouds. These clusters are loose associations of bright, newly formed stars that may eventually disperse as gravity weakens and the stars drift apart. They shine with the clear, energetic light of youth, dominated by blue and white stars that have not yet aged into softer colors. In contrast, ancient globular clusters surround galaxies like halos. These clusters contain some of the oldest stars in the universe, bound together in tight spherical groups. Their stars are dimmer and redder, having burned through their youthful brilliance long ago. Globular clusters act as time capsules, offering glimpses of what the galaxy looked like billions of years in the past. They orbit far from the galactic center, their stability preserved by the combined gravity of hundreds of thousands of stars packed closely together. These differences in stellar populations influence not just the appearance of galaxies, but also their color. Galaxies with active star formation appear bluer, filled with the light of young, massive stars. Galaxies that have stopped forming new stars tend to glow redder, their light dominated by long-lived stars that have cooled over time. Elliptical galaxies, for example, often appear soft and reddish because they contain older stars and little gas to form new ones. Spiral galaxies, with their active arms and rich reservoirs of gas, shine with mixed colors, blue in the arms, yellow and red toward the center where older stars dominate. Stars also help maintain the shape of a galaxy through gravity. Every star contributes to the gravitational balance that keeps the galaxy together. The combined mass of billions of stars forms the framework within which gas clouds move, spiral arms form, and clusters orbit. Even though an individual star is tiny compared to the size of a galaxy, together they create the gravitational field that defines the galaxy S structure. Yet, the most dramatic influence on a galaxy's shape often comes from a single object at its center, a supermassive black hole. These central black holes, weighing millions or even billions of times the mass of the Sun, sit quietly at the heart of nearly every large galaxy. They are not monsters devouring the galaxy from within. For most of their lives, they remain calm, influencing the galaxy mainly through gravity rather than through bursts of energy. However, when material spirals into the central black hole, the process can release enormous amounts of radiation, lighting up the galactic core. This is called an active galactic nucleus. In the past, when galaxies were young and gas flowed more freely toward their centers, these active periods were common. They may have helped shape the growth and form of galaxies by heating nearby gas, driving winds, and regulating star formation. Today, in most galaxies, these central black holes are quiet, exerting only their gravitational pull and allowing stars to orbit peacefully around them. The connection between stars and galactic shape becomes clearer when looking at how galaxies evolve. Spiral galaxies can slowly transform into ellipticals through collisions or mergers. When two galaxies collide, their stars do not typically crash into one another because the distances between stars are immense. Instead, the gravitational interaction redistributes their orbits. Gas clouds may collide and form new stars, but the overall structure reshapes itself. After the chaos settles, the resulting galaxy often becomes smoother and rounder, filled with older stars and less active star formation. In this way, the stars are both witnesses to and participants in the galaxy's transformation. Another way stars shape galaxies is through the energy they release. Massive stars emit strong stellar winds and ultraviolet radiation that carve cavities in gas clouds. Supernovae inject energy into the interstellar medium, stirring up gas and preventing it from collapsing too quickly. These processes help regulate star formation across the galaxy, ensuring that new stars form at a controlled pace. Too much star formation too quickly can exhaust a galaxy's gas supply. Too little can cause a galaxy to fade. The combined influence of stellar winds, radiation, and supernovae helps maintain a delicate balance. Over time, galaxies become patchworks of regions at different stages of stellar evolution. Spiral arms glow with young stars in active formation. The central bulge contains older, more evolved stars, the halo houses ancient globular clusters, and the quiet outskirts hold drifting stars that orbit at great distances from the center. Each region reflects a different chapter in the galaxy's life. The glow of a galaxy is, therefore, a story written in starlight. Its colors describe its age. Its shape reveals how stars have interacted over billions of years. Its brightness reflects the combined energy of all its stars. Even the quiet gravitational tug of its central black hole plays a role, guiding the orbits of stars near the core and shaping the motions of the galaxy as a whole. This way, stars are not simply inhabitants of galaxies, they are the architects. They illuminate the arms, define the structure, and influence the evolution of the vast islands of light that drift through the universe. And as galaxies evolve, collide, or slowly change shape, the stars within them continue their work, generation after generation, shaping the grand patterns we see when we look up at the night sky and trace the faint glowing spirals across the darkness. The slow, patient work of starlight is what brings the vast, silent forms of galaxies into being. The universe today is full of starlight. Every direction you look, if your eyes were strong enough, you would see the combined glow of countless stars scattered across billions of galaxies. But this bright, lively universe is only a chapter in a much longer story. Stars have not always existed, nor will they shine forever. Their future is shaped by the quiet but relentless changes happening across unimaginable expanses of time. If the night sky today feels eternal, it is only because human lives are so brief compared to the cosmic clock. When we widen our view to trillions of years, the future of stars becomes a gentle, gradual fading, a slow, peaceful dimming of the lights. Right now, galaxies like the Milky Way still have plenty of gas available to form new stars. In the spiral arms, cold clouds collapse under gravity, giving birth to red dwarfs, yellow stars, and the occasional brilliant giant. But this supply is not infinite. Every new star locks away some of that gas, turning it into a long-lived sphere of plasma. Supernovae and stellar winds return some material to space, but not enough to replenish the supply fully. Over billions and trillions of years, galaxies will slowly use up the gas available for star formation. The rate of new stars being born will decline, first subtly, then noticeably, and eventually dramatically. Galaxies will become quieter places, with fewer bright blue stars and fewer glowing nurseries. As star formation slows, the universe will enter a long dimming phase. Bright, massive stars will disappear first because they burn through their fuel quickly. Even today, they make up a tiny fraction of all stars. As the gas supply dwindles, fewer and fewer massive stars will form, leaving the universe dominated by smaller, cooler stars. The future cosmos will be filled not with blue giants but soft red glimmers. Red dwarfs will become the most common stellar lights, burning quietly across trillions of years while everything else fades away. Red dwarfs have always been the universe's patient stars, burning their hydrogen slowly and consistently. Because they use their fuel so efficiently, they can continue shining far longer than any star visible from Earth today. The sun is already in its middle age, but a red dwarf could shine for hundreds of times longer, outliving every other type of star. In the distant future, when star formation has nearly stopped and the massive stars have long vanished, red dwarfs will still be glowing softly. They will be the caretakers of the cosmos, providing the last natural illumination in a universe where new stars are no longer born. Yet, even red dwarfs cannot burn forever. Over trillions of years, they will slowly use up their hydrogen, becoming cooler and dimmer until they finally fade. Because none of the red dwarfs in the universe are old enough to reach the See late stages, we can only imagine what they will look like. They will grow fainter, turning from red to a dark ember-like glow. Eventually, their surfaces will cool until they no longer shine visibly, becoming quiet remnants in a darkening galaxy. As red dwarfs drift into their twilight, another population of stars will also be changing. White dwarfs, the leftover cores of sun-like stars, will spend trillions of years cooling. A white dwarf begins its existence tremendously hot, glowing with leftover heat from its former life. But with no fusion to sustain it, the white dwarf gradually radiates away its energy. Over incomprehensible lengths of time, it cools from white to yellow, from yellow to red, from red to a faint warmth invisible to the eye. One day, far beyond the current age of the universe, it will reach a temperature so low that it becomes a black dwarf, a cold, dark remnant containing the ashes of a long-dead star. No black dwarfs exist today because the universe is still too young. Even the oldest white dwarfs have just begun their cooling journey. But if we wait long enough, longer than any time scale familiar to the human mind, those ancient remnants will slowly disappear into the background. They will become dark, silent masses drifting through nearly empty galaxies, their presence detectable only through gravity. The universe will shift from a place of bright stars to one filled with cool stars, then fading stars, then only the lingering shadows of stars. As these changes accumulate, the cosmos will become quieter. Galaxies will lose their spiral shapes as new stars stop forming in the arms. The remaining stars will drift in wider orbits, and the structures we recognize today will soften and blur. Over time, galaxies will dim so much that even their brightest stars would be invisible to eyes like ours. The future night sky will not be filled with company. Constellations. It will be a sparse landscape dotted perhaps with the final red dwarfs still shining deep into their unimaginably long lifetimes. Eventually, even those last stars will fade, leaving only remnants. White dwarfs, neutron stars, black holes, and the cold shadows of what used to be luminous suns. New stars will no longer form. Old stars will no longer burn. The starlight that once filled the universe will become a rare treasure, fading into memory. For a very long time, black holes may continue to influence the universe, merging and shaping the darkness around them. But even black holes are not eternal. Over extraordinarily long time scales, they too will release their energy in faint radiation until they vanish entirely. The end result is not a dramatic finale, but a gradual quieting. The universe does not switch off suddenly. It dims slowly, gently across time spans so vast that they make even the age of galaxies seem brief. The cosmos becomes a place where energy disperses, where light grows weak, and where the once busy work of star formation settles into stillness. Yet there is something deeply peaceful in this vision. The universe began with violent expansion, intense radiation, and chaotic formation. Its middle chapters are rich with the brilliance of stars and the complexity of galaxies. Its far future will be quieter, but no less meaningful, a long, soft fading as the cosmos rests after ages of activity. When we look at the sky today, we are witnessing the universe in its luminous youth. Every star we see is part of a bright and vibrant moment in cosmic history. The future will come in its own time, stretching across trillions of years, allowing every last star to complete its story. And though the lights will eventually dim, the memories of their glow, the atoms they forged, the worlds they shaped, the lives they made possible, will endure in every corner of the cosmos. The universe's future may be a quiet one, but it is also a reflection of everything that came before. A long, gentle whisper, following a grand and brilliant song. Starlight may seem like something distant, something separate from daily life, something that belongs to the sky while we belong to the ground. But every part of human existence, from the chemistry in our cells to the warmth that keeps Earth alive, traces back to the light and matter given to us by stars. The connection is deeper than simple illumination. It reaches into the way our planet formed, the way our atmosphere behaves, and even the way human beings have thought, dreamed, and made meaning throughout history. Starlight is woven into our bodies, our cultures, and our imaginations. The soft glow of distant stars can evoke feelings of wonder, comfort, or reflection. The night sky encourages thoughtfulness, perhaps because it connects us simultaneously to the ancient past and the distant future. The light reaching Earth tonight from a distant star may have begun its journey long before humans existed. It is a message across time, a reminder of how small and precious each moment is. As the night deepens around you now, there is comfort in remembering that the stars continue their calm, patient work, regardless of distance or time. They shine, they evolve, they weave the elements of life, and they shape the galaxies that drift across the darkness. Their rhythm is slow and peaceful, a cosmic breath unfolding across billions of years, and even if some of them faded long ago, their light still travels onward, reaching Earth just in time for a quiet moment like this one. So, as this exploration draws to a close, feel free to rest in the gentle awareness that you are part of a universe filled with ancient light and endless stories. The atoms that support your body, the warmth that fills you, our room, and the thoughts drifting softly through your mind all carry echoes of stars long gone. There is something deeply soothing in that idea, something that invites calmness and reflection. If your eyes feel heavy, you are welcome to let them close. If your thoughts are still wandering, they may drift gently, following the slow pathways of starlight as it crosses the sky. And if you are simply listening, letting the rhythm of the words settle around you, that is enough too. Thank you for spending this time under the quiet glow of the stars and for allowing this peaceful journey to guide you toward rest. May your night be calm, your dreams be light, and your thoughts drift as softly as starlight on its long, patient journey through the universe.